this meeting here in CUCEI. And I will introduce you the Presidium. We have the honor to have here Dr. Marco Antonio Pérez Cisnero, is the rector, the dean of the CUCEI. Dr. Humberto Gutiérrez Pulido is the academic secretary of CUCEI. Dr. Oscar Blanco Alonso is the director of the Division of Basic Science. And from the organizing committee,
Vidwas, it's an honor to in the control cycle is for me as the one who asked the purpose of being here in this gathering in a little bit of minutes in advance. Well, first of all, I shall say CUCEI, our campus, is fully devoted to research. So that the activities like yours in this campus is actually holy. I use the word holy because we got more than 356 researchers on the National Mexican Register. That's just for give you an example, that's in comparison to other universities in the local ecosystem. The next one has only 44 researchers. We got 356. So imagine the colorful ecosystem of researchers and topics and subjects that we can manage in this campus. So for us, opening this conference is not just important, it's relevant. It's part of our whole life. And I want you to feel in that way. Please feel free to ask Professor Vidwas or anyone in the organizing committee if you want to have a short meeting with anyone in the campus, any other researcher of any other field, please ask them to organize this encounter, and that will be our pleasure. Please enjoy Guadalajara too. I was telling someone before that if anyone asks you if you want chili and any food, say no, because the chili in this city is quite a serious affair. So for me, it's only a matter of wishing you the best of useful contents and encounters between colleagues and the best benefit of this conference for all of you. For me, it's all I want to say. Thank you, Professor Vidwas, for all the organization. And hopefully this will be the first of many, many to come in the future. We also got many PhD and master students who I'm sure they will benefit of meeting with you, having a work, having ideas, new lights on the path for them. Thank you for being here in the city, and I really wish you the best for this conference. Thank you to all.
now from the organizing committee, we will have to Dr. Soham Viswas.
Welcome, everybody. First of all, on the behalf of the organizing committee, I would like to thank Dr. Marco Perez, all the authorities, Dr. Humberto and Dr. Oscar Blanco, for all the help, sponsorship, and all the support for last 6 to 8 months to make this thing successful. So now I would like to officially invite all of you. Okay, welcome being here. So I'm just the mentor member of one of the organizing committee. There are other members are Dr. Thomas Gorin, Dr. Pablo Lopez, and from UNAM Institute de Física, Dr. Dennis Boyer. So we will have starting our talk today at 10:30, and then we will have our lunch, and then we will continue for the other sessions. We have the short talk sessions today, And from tomorrow, we will start all the talks at 9:30. At 9:30 tomorrow, we have the keynote talk. And another keynote talk is on Thursday. That's also at 9:30. So other days, we will also start at 9:30. And the poster sessions are at Tuesday and Thursday. And our conference dinner will be on Wednesday. So on the behalf of the organizing committee, would like to welcome all of you again. Thank you very much for coming here. And we hope that we will have a very vibrant and very interesting discussions and sessions here for the next 5 days. Thank you.
You know, there is a Mexican custom to declare officially open a gathering like this one, and I will do so in this moment. No? If you can stand up, that's a way of showing respect in the Mexican tradition. And being the 9 hours and 50 minutes of this 1st of July 2024, is my honor and my privilege to declare officially open all the works on this meeting on complex systems and stochastic processes. For this institution and any of your institutions all gathering this morning. Thank you to all.
conditions in a few time steps. And the reason is because the distance between the trajectories grows exponentially by the Lyapunov exponent. And you cannot win from an exponentially growth. And the important thing to realize is that chaos is typical for physical systems. In quantum chaos, when I was young, people were arguing that quantum mechanics is linear, so there's no chaos. But you don't hear that anymore. And in fact, it was realized already very early on that in quantum mechanics, you can see exponentially growth via the so-called out-of-time order correlator, where you look at the wave functions where the times is in different order, it is out of order. And the way it starts deviating from the disconnected part is via exponential growth with a coefficient that is small of order h bar. And that is why the quantum Lyapunov exponent, which is the same as the classical one, is very hard to determine numerically for the system, because you have to find the behavior, the h bar coefficient. Very important is that for this for this Lyapunov exponent, there's an upper bound derived by Malacena, Schenker, and Stanford. It is equal to 2 pi kt over h bar, which roughly corresponds to the energy time uncertainty relation, where the energy uncertainty is kt, and so if you invert this relation, you get that one. So typical chaotic quantum systems, in fact, almost all systems are that. The oldest one people really interpreted like chaotic systems were nuclei. It could also be quarks inside the nucleon. It could be black holes. It also could be quantum computers. In fact, it are quantum computers. And all these systems, they are unpredictable. And the scale of unpredictability is given by the Lyapunov exponent. The chaotic many-body system I'm looking at is the so-called Sachdev-Kitaev model. And this is a model of n interacting Majorana fermions. And the Hamiltonian for this model is given by some random coefficients here. And these are Majorana fermions, the chi's. That means that these are anti-commuting matrices that square to 1/2. And in fact, this convention 2-1. And here you can represent them as Dirac gamma matrices in high dimensions. This is Q equal to 4 because there are 4, and you can expand them in regular fermions. These AK and AK dagger are the regular fermion creation and annihilation operators that satisfy this commutation relation. So this model does not conserve particle number. The Hilbert space is very large. If there are n of them, the Hilbert space, which you can easily see from just occupying the fermionic state, is 2 to the power n over 2, which I say here. The normalization is always such that the ground state energy of this Hamiltonian scales with n. This model was actually first invented by Annie Gervois in 1972. And people seem to systematically ignore that. And I don't know why. The model is explicitly written down in her paper. It was well explored in nuclear physics by many people around. And also the current community seems to forget that this is a well-known and well-explored model. For this model, you actually can calculate the OTOC. And in this figure, you see two cases. This is when you have only two fermions and interaction with two fermions, two-body interaction. And that corresponds to free fermions because you can diagonalize the random couplings, and then it is just occupying fermionic states in what you learned in high school. In out of order correlator, out of time order correlator, the one I showed a minute ago. I can go back if you wish. Oh yeah, there it is. This is the out of time order correlator. So that you have two fermion operators, 1 and 2. This is at time 0, and this is at time t. And the time dependence is obtained by Heisenberg evolution. And it is out of time order. If you would change the order, this is just, this one squares to 1/2, and it becomes a trivial correlator. It's just 1/4 if you calculate it. But out of time order, it is non-trivial, as you could see from the two figures which I showed here. This is for the integral system. And then what you see is that it goes somewhere and then it saturates. The points were obtained by exact diagonalization, and the curve, the black curve here, is an analytical result because these are free fermions. You can do everything analytically, which we actually did recently. This is for Q equal to 4. You have to do numerically. You cannot do it analytically. The curves are just lines, interpolations between the points. You can calculate the out of time order correlator, and it is really extremely hard to calculate the inverse Lyapunov exponent. These authors succeeded doing that, and you can already see if you look at the OTOC that basically these are not exponents. That's not an exponential function. If you ever do an exponential function, it looks very different than this function. It actually is very well fitted by a third order polynomial. And to still extract a Lyapunov exponent is just very hard, but these people succeeded that somehow, maybe with some bias, but it seems to work, and we also did that. Also, a non-zero Lyapunov exponent doesn't necessarily mean that the system is chaotic, as we know from work by Leah and collaborators. Instead of looking at the wave functions, when you look at the OTOC, a much simpler way is to look at spectra of quantum systems and to relate the correlations of the spectra to random matrix theory. And this was actually well known in the early 80s. It was well known by Savlatsky, by Michael Berry, he knew it. In Heidelberg, we knew it. But Boigas, Giannani, and Smith actually sat down, did a calculation, and made it very explicit that chaotic motion is directly related to random matrix statistics of the eigenvalues in a quantum system. And again, there are always exceptions, as was shown by Bennett, Levrin, and Seligman. You can construct integrable systems with random matrix theory. But generically, that is not the case. If a system is chaotic, the eigenvalues are RMT. Here you see the early examples by the Boigas group. One is for nuclear levels. This is a histogram of nuclear level spacing, which are given by the Gaussian orthogonal ensemble, one random matrix theory. And this is for the so-called Sinai billiard, where you also see agreement of the level spacing distribution with this curve, which is random matrix theory, while this curve is what you get from uncorrelated eigenvalues. So what's random matrix theory? First, I will tell a little bit about the classification. The most important thing about random matrix theory is universality. And I say a little bit about eigenstate thermalization. So in random matrix theory, we have 10 different random matrix ensembles. 5 of them, oh, damn it. Yeah, okay. Five of them are full matrices. These are these 5. 3 of them are the Wigner-Dyson ensembles, which are either real, complex, or quaternion real. 2 of them, then they are either symmetric or self-dual antisymmetric. There are also 5 ensembles which have chiral symmetry. That means there are blocks of zeros here and there. 3 of them are when these are real, complex, or quaternion real, and 2 of them, which were the last 2, were found by Altland and Zirnbauer, when these are either symmetric or complex anti-symmetric. They're all characterized by anti-unitary or involutive symmetries. So you get all of them by just solving for all anti-unitary and involutive symmetries. Random matrix theory is, but also non-Hermitian random matrix theory, but I don't discuss that today. There are 38 classes. The most important thing about random matrix theory is universality. And it is, I think, the strongest universality observed in nature. The universality of correlation functions between 2 close-by eigenvalues is seen in systems all over physics, from say the Rydberg state of hydrogen atoms to nuclear levels, to eigenvalues of the Dirac operator in QCD. So this is a very strongly universal property of quantum spectra. Another thing with universality is, which is often not emphasized, is that if you look at this sigma model formulation of random matrix theory, the spontaneous breaking of symmetry breaking is exactly in the same way as it would be in a QCD in the same symmetry class. So we also understand the wave functions in random matrix theory. In the wave functions, the unitary matrix that diagonalizes the random matrix decouples, the measure decouples from the measure of the eigenvalues, the Jacobian, and therefore the wave functions are just given by the Haar measure of the unitary group. And if you look at the distribution, it comes what is known as the Porter-Thomas distribution. And this was well understood in particular by French and collaborators who applied this to expectation value of operators in of operators in general. And they stated that there's a diagonal part when the states are the same, which depends smoothly on the energy of the eigenstates. And there's an off-diagonal part, which is 1 over n. N is the size of the random matrix, or the Hilbert space in general, times a random matrix. This property is nowadays referred to as eigenstate thermalization. And here I have an example, actually from my papers from 1982, where you see the magnetic moment of states in the nucleus as a function of the energy of those states. And you see a smooth behavior with Gaussian fluctuations around this smooth behavior. And that is exactly what we know from eigenstate thermalization. And as French and collaborators formulate that, if you look at an eigenstate of an operator, you can write that as 1 over d times a delta function with the Hamiltonian times the operator. So this is the microcanonical distribution. So the expectation value is equal to the microcanonical average. That's why you have eigenstate thermalization. But you can also expand this in orthogonal polynomials. And the first few orthogonal polynomials give you the smooth part, whereas all higher order polynomials, they give you the fluctuations around the smooth part, that is the Gaussian. And this is the derivation given by the point made by Dreyer, French, and Wang, which paper also became unknown to people who worked on it later. I think I skip the time scales in chaotic system. I just be very short on it. So the time scales are the Ehrenfest time. First of all, the Lyapunov time, the inverse Lyapunov exponent. The Ehrenfest time, that's a time scale when quantum fluctuations become macroscopic because of the exponential growth of the fluctuations. There's a Thomas time, that's a time scale when beyond which the evolution is given by random matrix theory. And there's the Heisenberg time, which is the inverse level spacing. For many body systems, you can have additional time scales, which I discuss later. But I don't want to say more about that because otherwise I'm running out of time. So I want to now discuss in more detail the SYK model and see how some of these ideas apply to the random matrix, to the SYK model. The motivation for studying SYK model, the first one was to okay. Okay, I have. Okay, I cannot have it bigger. Okay, we have to, maybe you have to sit, if you don't see it, you have to sit in front, unfortunately. So the motivation is, first of all, it's a model for compound nuclei, which was, or that is how these first models were formulated by French and co-workers. It's also model for many body chaos nowadays. What's very important, SYK model is a non-Fermi liquid. So everything what you learned in statistical mechanics of fermions is actually incorrect. The states are not obtained by filling fermionic quantum states by just putting 1 fermions or 0 fermions. And importantly, the ground state energy, the ground state energy of the system is extensive. It is not 1 or it's not 0, but the entropy is proportional to n. Also, the Mother-Sena-Schenker-Stanford bound is saturated at low temperatures for this model, and that is why people in the high energy community got excited about the SYK model. And that also gives you the connection to quantum gravity, which I also skip today. There are important limits. There's a limit when the number of particles is much larger than the order of the interaction squared. Then the eigenvalue density is a Gaussian. There's also a limit when the order is, when Q squared is much larger than n, then you are into the RMT regime, and there's a double scaling limit. And in this double scaling limit, when the Q squared of n is of order 1, you are able to solve the model analytically to a great extent. And here I give you the example for the random matrix theory. The spectral density is a semicircle, and in the double scaling limit, when Q squared over n is fixed. I forgot a slash here. The spectral density is a semicircle times some correction. And this correction, it gives you exactly the density function of the Q-Hermite polynomials, where E naught is the ground state energy, which is related to the variance of the Gaussian matrix element divided by some coefficient, which is related to how you commute Majorana fermions. And asymptotically, it is given by e to the power minus 2q squared over n. If you compare this to a numerical result where the red curve is the analytical result, and the black curve, the red curve is the exact eigenization result, and the black one is the analytical result. And here also the red one is the black one is exact eigenization, and the blue is numerical finite end calculation. And you see that the agreement is really very well. I also skip this. I cannot skip that. Okay. Yeah. So the point I want to make now is that a big difference is with normal random matrices, the matrix is full. If you have an n by n matrix or a d by d matrix, you have d squared independent matrix elements. That means that the error you make going from one realization to the next is 1 over the square root of d squared. That means that the eigenvalues typically move all together back and forth by order 1 over d. For a many-body theory, there are only n choose q independent matrix elements. That means that the error you make going from one realization to the next is 1 over the square root of n over q. And whereas the level spacing is the inverse Hilbert spacing is 2 to the power minus n over 2. That means that these fluctuations actually cover many level spacing. And that is why you see deviations because of these collective fluctuations. You see deviations from random matrix theory very early on. Because if the effect blows up by order 1 over n over q over 2, if you look at q over 2 level spacings, it becomes of order 1. So the time scale corresponds to that. It's 1 over n to the power q times the eigenvalue spacing. This is the Heisenberg time. So it is the Heisenberg time divided by n over q. This is the time scale of the collective fluctuations. And you can only see RMT fluctuations beyond this time scale in many body systems. What it has become popular today, if you look at eigenvalue correlations, is to look at the spectral form factor, which is the Fourier transform of the pair correlation functions. And it is given by a straight line for the Gaussian unitary ensemble and then a constant. And this is the orthogonal ensemble, and that's a symplectic ensemble. And if you compare that to some exact results, and here you see a typical comparison for the SYK model, where actually I threw out the collective fluctuations. And the agreement is really very, very good. I cannot magnify that, but if you would magnify this by a factor 10, you still would not see any difference between the analytical result and the numerical result when there's no fitting, but there's filtering going on. You could also do something else. You could, instead of unfolding the eigenvalues, that means mapping all eigenvalues to eigenvalues with unit level spacing, which I did in the previous figure, you can also fold in the average spectral density in the correlation function and compare that to the raw data, which are the black lines here, compared to the analytical result. And then you see a perfect agreement without any fitting. You just put in n equal to 26 and q equal to 4 in this case. And we also have full control over the collective fluctuations. This is for the symplectic case where there's a peak in the correlator, and you see that it agrees, the spectral form factor agrees with great accuracy with the analytical result, including scale fluctuations. In the last, I guess, already few minutes, I will mention a little bit dissipation in the SYK model, where we have studied the Lindblad equation for the SYK model, where the density matrix evolves according to the Liouvillean. This is an SYK Hamiltonian, and these are jump operators in a Lindblad equation. And we use linear jump operators, which are linear in the fermions. Then the large time state is just given by the identity, because L squared is 1, that is 1, and the identity commutes with the Hamiltonian. One way to study this equation is by vectorizing the system. That means you map the density matrix to vector, so you flip a bra to cat, and then the Liouville operator is given by the difference of two SYK matrices and an interaction term due to the jump operators. So this operator is equivalent to this operator. It has this, if you know the solution of this, you know the solution of that, and vice versa. This is a non-Hermitian system for which you can study the relaxation rate. You can study operator growth, for example. You can also look at effects of topology, which we did recently. It is a non-Hermitian model. The ground state is given by just the identity, which we call the thermal field double state. There's the ground state at 0. There's an exact many body scar at -4 mu, and these are non-Hermitian eigenvalues with a finite there's a finite distribution. And the surprising thing about this model is, if you look at the relaxation rate to the ground state, there's a phase transition as a function of the strength of the jump operator. So it goes up linear, there's a phase transition, and then asymptotically it goes to the analytical result. And the curve is the solution of the Schwinger-Dyson equations. The last two slides is about a remarkable relation with topology. And in this model has actually a non-invertible involutive symmetry. If you look at the Lindblad operator and you commute it with a projected swap operator between the left and the right SYK model, you get L dagger times the same projected operator. It is non-invertible because there's a projection, and Q swaps the left and the right fermions of the model. The square of this is equal to 1, so it is an involutive symmetry. And what you can do is you can look at, because of this, the operator PQP times L is Hermitian. That's why it's pseudo-Hermitian operator. So you can look at the eigenvalue flow of PQP times H, which is actually this H is L, which is Hermitian plus M, and we look at the flow of the eigenvalues with M which you see in this figure. And what you see is you see states that flow from minus infinity to plus infinity like that. But there are these states. These are topological in nature, because if you do it any deformation, these lines you cannot get rid of. They remain. If you change the coupling strength, you see exactly the same lines. They are still there. They are deformed, but they don't go away. They are topological, and they are always, I don't remember in this case, they are probably exactly 64 of these lines. These lines are degenerate, and it is 64 because that is 2 to the power n over 2. Then it should be 32, so I may be wrong. So that was all. I have some conclusions. First of all, RMTs are strongly universal. In many body systems, there are only a small number of non-zero matrix elements, which has important consequences. And that is why there's a torus time of the Heisenberg time divided by n to the power q over 2. We have seen anomalous SI dissipation in an SYK model coupled to the environment in a Markovian way. We do not really understand the nature of this phase transition very well, but it's a very significant phase transition. And there's also a remarkable relation with topology, which we are still exploring further, just as today. So that's all. What?
Yeah, there. So can you explain again, you're using the SYK model, right? And what is the L and the L dagger? Ah, there it is. Okay.
Yeah, L is just a fermion operator. I call them also chi.
Okay.
This is an element of Clifford algebra.
Okay.
It's a 2 to the power n over 2 times 2 to the power n over
The one that you wrote, right?
matrix.
And then the Liouvillean operator there. This is yeah. This equation, is it well known? Is it obvious?
And it's kind of obvious because this acts both on the right and on the left, and you change actually a matrix into vectors.
Right.
And by acting on the left, you get, because the commutator, you get the minus sign, then you get this or this, and if you act on the right, you get this.
Okay.
So you actually have to work through it, doing this transformation, that this is exactly that. It is well known to people to whom it is well known, I would say.
Fine, okay. And then you just went on diagonalizing the operator, and that's where you get information about the phase transition.
Yeah,
okay.
That's right. We looked at what we did is we derived a Schwinger-Dyson equation for this Liouvillean. That's one thing. The other thing is that we also did exact diagonalization. We actually solved it in different ways. We solved it in Euclidean space and also in real time. And we also did exact diagonalization. I actually didn't show those data. And there's another way. You can also solve this equation directly. This is just a differential equation. And you can solve it directly. And we're also doing that. But we didn't publish that yet.
So just one, and then the information about the phase transition, what is the quantity that you measured that indicated that there was a phase transition?
That is, if you look at the Green's functions of this system, that is psi t, psi 0. That is the Green's functions. We look at the decay rate of the Green's function. And the remarkable thing is, it is on the next slide, is that, it is here, oh, it is further. That the decay rate in the limit of zero coupling is actually finite. So it doesn't go to 0. At When you have a finite system, it is actually 0. So you actually have kind of spontaneous symmetry breaking in the decay rate. As soon as you have an infinitesimal amount of coupling, then the decay rate actually becomes finite. And if you do finite size scaling, you see nicely that it converges. It actually converges very badly from finite n to this infinite n limit obtained from the Schwinger-Dyson equations.
Thank you.
Thank you very much. I have two questions. One is more technical, and the other is perhaps more philosophical. And the technical questions, you mentioned that the positively Lyapunov exponent not necessarily means chaotic behavior, if I remember correctly. And I'm wondering about this statement. How is this possible?
You have to really discuss with Leah,
Okay.
who wrote the paper about that.
At a critical point, you can have instability without.
Okay. Okay. And the more philosophical question is, to what extent do you consider these systems, their behavior, as deterministic chaos? So it's chaotic, I understand, but whether you consider it deterministic chaos or not?
We have ensembles, whether you could say whether that is deterministic or not. So you could look at whether there's what we call ergodicity of the ensemble, whether one member of the ensemble already has the properties of the total ensemble. This is true for the spectral density. If you look at one of them, it is exactly equal to the full ensemble average. If you look at the OTOC, if you look at one of them, it fluctuates wildly, orders of magnitude, and the average, in the beginning I showed you a figure, the average is maybe over 1,000 or 1,000 members of the ensemble to get the fluctuations down. And in some cases, we have to average over 10,000 to get the fluctuations down. So there's no echo. The OTOC is not self-averaging.
Thank you very much. Thank you.
Well, is another question?
Was there a particular point of why to choose this kind of dissipation with this Limblad operator, C alpha?
Oh, this Markovian. We are going. That's simple. Markovian. So you don't. The real point is that you don't have to consider the path because it is Markovian. You can actually get an equation for the density matrix only in terms of the Bath degrees of freedom. And the reason for us using the jump operators we did, linear jump operators are just simpler. These are the simplest possible, so that's why we choose them. We also looked at quadratic jump operators. We also classified all type of Lindblad operators you can get based on the evolutive symmetries by looking at art order jump operators. So we looked at many different cases, but these are the simplest thing.
The phase transition appear in all of them? I mean, this is or it depends really on this particular choice of
we don't know that yet. We don't know. We only did a detailed analysis for the simplest case.
Okay.
Well, then, thank you again, Jacques, for your talk. Give you the certificate.
Thank you.
Okay, our next speaker is Hernán Larralde from Instituto de Ciencias Físicas de la UNAM in Cuernavaca. We are very happy to have you here, and please Start your talk.
Bueno, sí, bueno. Okay, well, let me begin by thanking the organizers for inviting me here to this event. As Thomas said, my name is Hernán Larralde, and I work at the Instituto de Ciencias Físicas of UNAM in Cuernavaca, Mexico. Those who don't know it are welcome to visit whenever you want. And I'm going to talk about some results we obtained with some colleagues, Satya, who's over there, and to whom all questions should be addressed, please. Gregory, the student Marco, and more recently was a postdoc called Roberto Mota back at the Institute. Let's see, how does this work? It doesn't work. Oh. It always happens. Ah, there. So, now, hey, it's going to get to the end. Okay, so the details of these results can be found in these only 2 papers, not like Professor Jacobus, who showed us results over a lot of papers. This is much simpler stuff, but it's relatively recent. And I'll also be talking about universal properties, much more basic universal properties. We all know that, for example, the sum of random variables in the limit of large number of variables is given by, well, it's described as the subject of the central limit theorem. And this is, of course, a very universal result, statistical result. And also, the Fisher-Tippett-Gnedenko theorem, which is related to the extreme values of independent, identically distributed variables, right? And of course, I don't need to tell you the importance of adding random variables. That's the basics of all random walks, for example, and all the things that can be modeled by random walks. And the statistics of extreme events, well, there's a hurricane coming, and you want to see extreme events, wait a few hours, and we'll see some very extreme events. But of course, always there's this thing about a chain is as strong as its weakest link. For example, this is obviously another example of extreme value statistics. So the importance of these results, of these statistics is rather clear and obvious. Staying in familiar grounds, of course, the central limit theorem, I know most of you, or almost everybody knows this, but still, is that if we have a set of n independent identically distributed variables drawn from a common distribution phi, say, and this distribution has mean mu and a variance sigma, then the sum of these variables doesn't work. Now it works. So it's okay. The sum of these variables becomes Gaussian distributed in the limit of a large number of terms, right? And this center limit theorem has been generalized in many ways. A particularly useful and popular one is that if the distribution does not have a finite variance, then the sum of the variables does not become Gaussian, but rather it goes to a Levy alpha stable distribution. And there are many other interesting generalizations. A little bit less well known, perhaps, is the Fisher-Tippett-Nedenko theorem, which again states that if we have n independent, identically distributed variables drawn from a common distribution, and we define y as their maximum, then there exists scaling factors, non-universal scaling factors, an and bn, such that shifted and rescale probability distribution will tend to a function that is independent of n as n goes to infinity. And the theorem states that g of c can only be of one of these three forms, which is a Gumbel distribution, a Frechet distribution, or a Weibull distribution. So the complete statistics of sums or of extreme value statistics are described by just a handful of universal distributions, right? Gaussian, Levy alpha stable, Gumbel, Frechet, and Weibull. That's it. That's it. That's all the distributions that describe an enormous amount of systems. And actually, we can extend these a little to what Satya likes to call weakly correlated random variables, which, I mean, roughly speaking, we can think of as, again, a set of n variables whose correlation function decays quickly over a certain correlation length psi. For example, we can have this kind of exponential decay in the distance separating variables xi and xj. Now, so what happens here, of course, is that if two variables are separated over a scale z, which is much greater than the correlation length, then they are essentially uncorrelated, right? So if we have enough of these variables, we can divide the system into n prime blocks of size z much larger than the correlation length, and those blocks will contain essentially independent variables, right? So after that, if we just denote yi, the maximum of the variables in block I, and si, the sum of the variables in block I, then the maximum over the complete set will also be the maximum over the set of y's, and the sum over the complete set will be the sum over the si's. So again, in this case, we expect that the extreme value in some statistics will be given by the universal distributions. So these are extremely powerful and universal things. So what happens when one has strongly correlated random variables? And here again, copying Satya, I'll call strongly correlated to a case where correlation prevails over the whole set of the variables. So you can't break them up into sets that are essentially independent from each other. And as you probably know, there is no general theory for the extreme value and some statistics for this kind of variables. And what we can do, or the best thing we can do instead, is to try to study different instances that can be solved exactly and hope to gain some insight into how to deal with these kind of problems. So that's exactly what I'm going to talk about now. Right? We're going to talk about two simple, actually relatively simple cases of strongly correlated variables that are exactly solvable, and I'll try to make some time to show a simple application of these. So let's begin with a couple of cute examples. Let's consider a set of n real positive variables with this joint distribution function. Okay, this is relatively simple, and it's very obvious that the distribution does not factorize in any way, right? There's no approximation in which this distribution can factorize. So, these variables are clearly not independent. No, they are. However, it turns out that this distribution, it's very easy to show that the distribution of the maximum of these variables, with this common distribution, has this form, right? The joint, the cumulative distribution function. It actually looks a little bit like a Fréchet distribution, but that's just a coincidence, I think. Not only that, but if instead of trying to describe the maximum of these variables, we were interested in, say, the minimum as an extreme as well, then it turns out it's even easier, and this is the exact density function for the minimum value of these x with that that joint distribution function. And we can also calculate rather easily the sum. If we define y as the sum of these n variables, then the distribution of this sum is given exactly by this expression here. Okay, so that would be a first, say, cute example. Another one, not as cute, I think, would be this one. Again, we consider, say, n real variables. Now, they're real, not necessarily positive. And we assume they have this joint distribution function where k is the modified Bessel function of order n-halves minus 1. And, well, okay, it looks really ugly, but it turns out it's very simple again. Even though it's clear that the distribution does not factorize, and these are not at all, or in any sense, independent random variables, their maximum distribution, the distribution of their maximum is given by this expression and the limit of large n. And the distribution of their sum is just a double-sided exponential, very in the limit of large n again. Okay, so something's fishy. Obviously, there must be something fishy going on. Why are these variables easy, even if they are not independent? What's going on? And it turns out the explanation is really simple. These correlated variables can be analyzed completely or solved, in a sense, because they are conditionally independent random variables. That means that there is a parameter, lambda, which may or may not correspond to a actual physical parameter, such that if you fix lambda, then the variables are independent. But lambda itself is distributed according to a distribution phi. Okay, so while fixing lambda gives rise to a set of independent, identically distributed variables, once we integrate over this parameter, then the resultant distribution is not, in general, factorizable, and this integration induces, if you like, correlations among these variables. Specifically, the examples I showed you correspond to a conditional distribution, which are just exponentials, right? With a rate lambda, and the rate lambda itself is exponentially distributed. You do that, you get this joint distribution function of correlated variables. But they are easy to solve because you can focus on them for fixed lambda and then integrate. Similarly, the other example I showed corresponded to Gaussians, conditioned distribution were Gaussians with variance lambda, and again the lambda was chosen, the variance was chosen to be exponentially distributed, and that's what gives rise to this ugly expression. But again, this is the secret behind the fact that these variables can be solved completely. So they can actually be solved completely. And I won't show you all the results, of course, but we can find the complete bulk order statistics. For example, what is the distribution of values for the 50th or the 80th or the K value, not only their extreme value statistics, which correspond to the smallest or largest values, and which sometimes cannot be extracted directly from the bulk order statistics. And of course, my favorite is that we can also analyze the statistics of the sums. So we can actually find the complete statistics of random walks, for example, that give steps that are correlated by these kind of distributions. Now, what turns out to occur, and what happens here, is that the resulting statistics of these conditionally independent random variables are very strongly dependent on this distribution here. And that's kind of a bummer because it means that we no longer have these nice handful of universal distributions that describe everything, these 6 or 7. I thought you were going to say my time was over. So yes, okay, I was saying we don't have this handful of distributions that will describe extreme values or some statistics in general, but all our results will depend very crucially on the value of the distribution phi. So I won't bore you with all the details, of course. I'll just give you some of the flavor of what kind of results we obtain. For example, this is what would happen if these conditioned distributions had this form which corresponds to the Gumbel family of extreme values, which is basically a stretched exponential with some prefactors. And the big problem here is that this parameter on which you're conditioning can appear in the normalization factor, in the exponent of the prefactor, in the generalized rate, or in the exponent of the stretched exponential. So we have to take care and follow what happens with each of these possible dependencies. And it turns out that in the limit of a large number of variables, we can calculate the probability distribution for the largest value, the extreme value of these variables. And it's given by this ugly expression here, where phi is the distribution of lambda. Phi, this is the same phi. An is this function given in terms only of the generalized rate and the exponent gamma, lambda star are the solutions of this equation. You have to solve the equation. You evaluate the phi at the solutions, divide by the Jacobian, of course, and add overall possible solution. This is the expression, the general expression for the extreme value, the distribution of the extreme value of this set if the conditioned distributions are given by this expression. I'll talk a little bit more about sums. I like sums. I like random walks. This is what I like. Satya like extreme values. So I'll talk about the simplest case again, which is when these conditioned distributions have finite variance. So mean and variance are defined. And if we denote S as the sum of these variables, then it turns out that the distribution of S is given by a very similar expression to the previous case when the mean, right, the derivative of the mean is not 0. If this is the case, then the distribution of the sum of these variables is given by this expression, again, in the limit of large n's. And where that looks ugly, it is easy to see, for example, that the moments for this this distribution are given by this expression. Basically, we get ballistic scaling, which means, of course, that the nth moment scales like the nth power of the number of steps, or the number of terms in a sum, and with a coefficient that is given by the average of the nth power of the mean. And it's averaged over only the distribution phi. And from there, we can also infer that the distribution of the sum has, in the limit of large n, will have this kind of scaling. Okay. If instead we have a case where the mean is 0, right? If the mean value of these distribution is 0, then this expression cannot be reduced easily, and one has to calculate this integral case by case for each choice of the phi. However, what we can do anyway, and it's rather trivial, is to calculate the moments for this. And now, before we got ballistic scaling, but now we have diffusive scaling, right? Since if the mu is 0, these distributions become symmetric. The odd moments vanish, and the even moments, moment 2n scales like the number of steps to the n, but it is no longer a Gaussian. We have diffusive scaling, but not Gaussian distribution. And but we can also easily show that the correct scaling for this variable, for the distribution of this variable is given by this expression. So let me just briefly, we still have time, briefly talk about a simple application of these results. And this is really recent. It's like from 3 days ago. So what we have here are the returns at 1 minute spacing of apple stalks, not the fruit, but the computers. And we can see here we've got what, like 16, 18 years, And these are minute by minute returns. This is a lot of data. It doesn't appear as that much, but it's a lot of data. And you can see that in some periods of time, the volatility, which is basically, in this case, we took as standard deviation of this data, goes through periods in which there's high volatility, and then there's a few months of low volatility. Low volatility, that would be perhaps a month, then high volatility for a few months, and so on. Okay, so that's how it looks like. And we could be interested, for example, in finding out the distribution of returns over a certain period of time. If you invest, one should at least care about the distribution of returns of your investment. So we measured the returns of your investment, the distribution, the complete distribution of returns at 1 minute, which is the first curve, then at 10 minutes, 30 minutes, 60 minutes, and so on. And we see, of course, that the distribution depends on the time interval, as it should, obviously, right? And then there's this thing: how do we connect the returns in one scale, say at 60 minutes, with the returns at 1 minute? And the efficient market hypothesis, basically, in its simplest version, says that the return, the price, or the earnings in the stock market are a random walk of the returns. Just add returns. That's it. No? Now notice these are returns over periods of time that are very small compared to any scale here, right? So what we'll do, or consider, what we think we're doing, we're not sure, is that when we calculate these returns, the volatility over this period is essentially constant. Okay, that's the whole idea. And we're adding, to get the complete distribution, we're adding returns, or putting together returns from times that have very, very different volatilities, very different variances. Okay, so if that's the case, then this should correspond to our result here, right? We can, over these intervals of time, the mean value of increase of the stocks is essentially negligible, right? So we expect to find this the distribution, and indeed, if we rescale all these according to diffusive scaling, just the normal diffusive scaling, we get a pretty good collapse, I'd say, for something done three days ago. That's not bad. And we can do a little bit more, I think. Now, we went on and measured the distribution function of the volatilities. Now, again, defined as standard deviation over a period of time, because I mean, you can't define the standard deviation at one point in time. So we take a period of time. Here it's a day. It corresponds to 8 hours, quite a few minutes. And we calculated the whole distribution of the volatilities for that data set. And we find this figure, which has a reasonably good, I guess, power law tail, with an exponent given by as minus 3.5 approximately. In the literature, 3 to 3.5 values for this are very common. And again, according to our results, then the distribution function of returns will have that behavior. That's what we would expect. So we do a log-log plot, and okay, that's the same. That's a line with the same exponent. We see it's pretty good. I mean, if you don't mind my saying so. Here is a semi-log plot because it looks cool, and it shows that this power law result actually covers a very wide range of values, I think. This is Bitcoin returns. This is not Apple, but now it's Bitcoin. We don't have as much data, so here these are returns at 1 day scale. Now the others were at 1 minute scale, so we don't have that much data. But we can see anyway that it looks qualitatively different. The returns for the Bitcoin than for Apple. And we can try to do the same thing, and we see that the distributions, of course, don't, well, sorry, that's not what I wanted. Shit, not so fast. The distributions looked qualitatively different, and a reflection of that difference is the fact that the distribution now looks very much like a double-sided exponential, and here we only have 2 times because our time interval is 24 hours, so we can't do much better. If we do longer times, we have very little statistics. Looks exponential, kind of. We have to admit that these guys are really bad outliers. But okay, but that's the data. That's what came out. Okay, and we don't have enough data to make a reasonable connection between the distribution of volatilities and the shape of the distribution of returns, because our data isn't good enough yet. This is semi-log and a log-log plot. Certainly not a power law, but it's not an exponential either, so we're still working on it. So with that, I'll finish. The idea, central point, is conditionally independent random variables, like the kind I showed you, are very simple generalizations of independent, identically distributed variables. And as such, they can be treated with basically the same kind of tools. They give rise to a huge family of correlated random variables that can be easily treated. They appear naturally in sampling over heterogeneous environments, like I showed you, like this case for the returns. And they also appear in mean field theories. There was also an example on a random matrix theory. And unfortunately, the statistics depend very crucially on the form of the distribution of the parameter. So there are no simple asymptotic distributions describing this kind of statistics. And with that and in time, I want to finish. Thank you.
Other questions?
If you convert the Apple data to day-by-day data so that you can compare directly to Bitcoin, how does that affect the distribution?
No, it just reduces our data set. But yeah, we tried that just to see if the differences, what I said were qualitative differences, were not just an effect of that. But no, it just actually, you can't really tell the difference because the scale at which I plotted the apple returns has 18 years. So if you cut what happens in the minute scale, but it really doesn't show any difference.
Okay. Any more questions?
So I was wondering, is there any understanding of why in the two cases the distributions are so different? I mean, eventually the end results that you get are quite different.
In which two?
The Apple and the Bitcoin.
Okay. I won't pretend I understand finance at all, but there are several things. I think the people who trade on Bitcoin and people who trade in Apple are different investors. There's these things called sophisticated investors, and there's a lot of amateurs in Bitcoin. There's also the fact that Bitcoin is closer to Forex, foreign exchange, than to stocks and bonds. And it means also that there are people trading 24 hours a day. People not here, but here they trade some hours, and then in Asia they trade other hours. And it's the same as in Forex. There's a much larger community and dispersed community trading Bitcoin and other coins. So those are our guesses, but I admit they're just guesses.
Okay. Any more questions? Oh, sorry.
Have you looked at the cases where this distribution phi of lambda is anomalous, for instance, has no mean or variance?
Yes. Yes. We get other very funny distributions. Like, for example, I showed you one with a power law, but right now as a fit for Apple stock. But you can choose very many. They don't change the scaling. The scaling was the number of steps that never changed. You will change the shape of the distribution, but not the scaling. Okay. You always get normal diffusion.
Okay.
Well, thank you again, Hernán.
Okay. That's it.
Okay. Well, our last speaker for the morning session is Markus Müller from UAM, so the State University of Morelos, Cuernavaca, and he will talk about Fourier phases.
So thank you very much for this kind invitation here in Guadalajara. I'm very pleased that I have the opportunity to tell you a little bit about what we are doing and what we are doing concerning nonlinear time series analysis. And well, Professor Verbaarschot talked about a lot of papers, and none about 2 papers. I'm still more modest. It will be just one work, which I'm going to present. And the main work, the hard stuff, was done by Antonieta Martinez and Alberto Isaac Aguilar, 2 ex-PhD students from us, and a close collaborator is Gustavo Martinez-Meckler from the Instituto de Ciencias Físicas in Cuernavaca. So nonlinear time series analysis, we know what means linear relationships. Linear relationships, there we are just quantifying how similar is A with B. I mean, the weather tomorrow probably is quite similar to the weather today. Well, with climate changes, I don't know, but that's another subject. So we are just quantifying the similarity between two quantities, or within the same quantity, a time lag further. And here just an intuitive example of a nonlinear alpha correlations that are data from an NMR laser, a picture taken from a very nice book written by Holger Kanz and Thomas Schreiber. And we can see the amplitude of the laser at one time step as a function of a time step further. And we can see that there's a quite fancy interrelationship, which is not just A is equal to B, and although this nonlinear component within a complex system might be quite small, that doesn't mean that it is not important. So it might be interesting to reveal at least some nonlinear features from time series in order to get some insight to some interesting dynamics. So what that means that we have, in some sense, evaluate or to characterize the topology, the structure and phase space of a system. And usually we don't have an access to that. We have access to time series, which is actually a projection and phase space as indicated by this illustration of the simple system of a harmonic oscillator. So direct access to the phase space we do not have, but this would be necessary in order to reveal, to extract nonlinear features. But thanks to the theorem established by Floris Takens at the early 80s, there is a possibility to reconstruct a phase space which is topologically equivalent to the real one under certain circumstances. So let's assume here the time series of the harmonic oscillator, and then we are putting two balls on that in a certain distance, a red and a blue one, and let's understand that as a two-dimensional, the components of a two-dimensional vector, so a red component and a blue component, and then we just move the dots along the time series, and then what we can see is that we are able to reconstruct this phase space. Of course, this is a very easy example, and I knew beforehand that the dimension is two-dimensional, and I knew how to select the distance between these dots, and these are the two crucial parameters which have to adjust it. And that is another numerical example of the Rössler system. And some reconstruction of the Rössler system. One can see that it is geometrically different, but topologically equivalent if you're assuming the correlation dimension, or if you're estimating the Apunov exponent, it will be the same in both cases. So that is a good news, and the main message of the theorem of the Takens theorem. But what happens if the time lag is getting too small? Then we are just putting all these dots across the main diagonal in this reconstructed phase space, and we are not able to unfold the whole structure. Although that is a less delicate parameter, because we can just take the alpha correlation length or the auto mutual information length as a parameter, as a good estimate for the time lag between the dots. More delicate is the dimension, the embedding dimension. So it is evident that if we are choosing the embedding dimension too small, then we have we get crucial errors in estimating any kind of parameters from this reconstructed phase space. So that would be not very convenient. But if the embedding dimension is too large, it seems that it doesn't matter if you are calculating things like the dimension of the attractor, Although if you're interested in Lyapunov exponents, then there occur spurious exponents because of these additional dimensions which have nothing to do with the real dynamics of the system. And that is quite delicate issue to estimate the embedding dimension, at least for systems which have a larger dimension, let's say 30 or 40, even not talking about a system like the brain where you have probably a dimension of 10 to the 11, right? So beside of that, all this issue is quite sensitive to noise. That is again the example of the Rössler attractor, and I think I added a 1% noise level. The signal to noise ratio is about 100 in this example. If you like to estimate the embedding dimension, the attractor dimension, then it is hopeless. So what one needs is a stationary, probably low-dimensional system with a very low noise level. That this, in order to make this procedure work appropriately. And that are three conditions which are usually not met in biological systems, right? So, so I would like to make some advertising for this book of Holger Kanz and Thomas Schreiber, especially for young people which like to be introduced in this field. I think it's written in a very nice way and comprehensive and nice way, and beside of that, it's precise. So. The question is whether there is some way to get at least some access to nonlinear properties without doing all this very complicated stuff of a phase space reconstruction. And I think the one way of getting access to that kind of information is given by the Fourier phases. So the Fourier transform is bijective, so the information contained in the time series is given also in Fourier space, but the Wiener-Khinchin theorem tells us that the Fourier transform of the autocorrelation function is just the power spectral density. What that means that the information of linear autocorrelations are just imprinted in the Fourier amplitudes. And probably the most interesting information in Fourier phases, let's say information about determinism, phase-space structure, nonlinear autocorrelations, etc. The main idea is to focus on Fourier phases and derive some strategy to extract information from the sequence of them. And in order to illustrate the information contents of the Fourier phases, we did two numerical experiments. That is just the time series of an auditory signal. Maybe we can activate the first panel over there. That's just an English spoken phrase. No? Doesn't work? So one can see maybe in the time series there's this signal over here with some bumps, with some silent periods, and then we did two numerical experiments. We did a Fourier transform, and one time we didn't touch the Fourier amplitudes, but replaced Fourier phases by independent random numbers uniformly distributed between 0 and 2 pi. And that leads to the signal you can see on the bottom. And that is just noise. And if you could activate it, you would hear just noise, like that. But it has the same. autocorrelation function as the original system. And in the second, we didn't touch Fourier phases, but put all Fourier amplitudes equal to 1. So we did it like a white noise spectra. We destroyed all linear autocorrelations. And if we could activate this one could hear precisely the phrase. I have another example with but I mean, I'm even not able to go to the next slide. Yeah. So there's another example. There's a photograph from this beautiful horse, and then we have this watch and a book over there, and we did a two-dimensional Fourier transform of that, and then we're exchanging Fourier phases and Fourier amplitudes. So what you can see over there, that are the Fourier phases of the watch and the Fourier amplitudes of the horse, and here vice versa, and you can see the enormous information content in Fourier phases. So the question is why people are not focusing on Fourier phases. Everybody is looking to power spectral densities, etc. And the reason is maybe given in this figure over there. So we can see here the power spectral density of the Ressler system and the Lorentz system, and that are curves which are very easy to interpret. I mean, that is just the intensity or the energy with one certain Fourier component contributes to the constitution of the signal. And over there we can see the spectrum of Fourier phases, and they look quite noisy. I mean, it seems to be that it's not that easy to extract information from this mass. And so some time ago we got some easy idea, but it's just, I mean, just one proposal, and I'm very sure that if one is thinking a little bit more about that, one can have some much more fancy and more interesting ideas about that. So let's suppose we have two time series. Let's start with the bivariate case. And so we are doing the Fourier transform of that, and we get two sequences of the Fourier phases for each of the signals. And then we can understand that as two-dimensional vectors at some plane, but of course the plane is not a plane because the 0 and 2 pi direction points to the same, the 0 and 2 pi points to the same direction. So in reality we have a torus. So what we can see here is somehow a walk on the surface on this torus over there, right? And the idea is to look for correlations in this walk over the surface of the torus. And for doing that, let's say that is the point for the first Fourier frequency, for the second one. So it's one step on the torus, and then we are going to the next dot over there. That is the corresponding dot for the third Fourier frequency, and then we are just focusing on the deviation angle of this walk, and then we are looking for correlations in this walk upon the torus. So if this walk is completely uncorrelated, then the sum will be very close to 0, and J takes high values. If there are strong correlations within this walk, this sum might tend toward 1, and J takes small values. But of course, for any finite size of my walk, it will not precisely 1 and will not precisely 0, etc. So we have to fix some significance level for this measure, and usually one is doing that using Fourier transform surrogates. So one is has a time signal, one is doing some Fourier transform, getting the amplitudes and the phases, and then one is replacing the phases by random numbers uniformly distributed between 0 and 2 pi, and then we make the back transform and we get the first surrogate, but then because of the deficiencies, numerical deficiencies, the amplitude distribution is not equal to that of the original system. Someone is adjusting here the amplitude distribution to the time domain. That deforms slightly the power spectral density, and so in an iterative way, one is adjusting the amplitude distribution in the time and the Fourier domain. And if one meets some condition, one is just cutting this iterative process, and then you have to produce some ensemble of these kind of surrogates, analyzing them in the same manner, and then you're looking if there's some significant difference between the original system, the original results and the surrogates. And that you have to do, I mean, if you're thinking about, let's say, analyzing the whole night recording of an electroencephalogram of a person, that you have to do with a running window approach. So you have to generate for each running window an ensemble of these kind of surrogates in order to fix some significance level for your results. Well, in our case here, we can just make a random walk about a walk about random numbers given here, right? And that would give us the null hypothesis or non-correlated walk upon the torus. And that we did here with this curve. So for the x-axis here would be the length of the data segment you are considering. And then we are doing 100 random walks about this torus and looking for the minimum value, and that is indicated by the green line here. These results here are just the results for one trial. You may also create an ensemble for that, for different kind of segment lengths. And the great advantage is that this you have to do once in your life. I mean, that would be the valid curve for any kind of data. I mean, if you have an electroencephalogram or seismogram or financial data or whatever, that you're doing just once, and then you're looking if your results you're deriving are below this curve or not, and then you can be sure that your results have a significance level of 1%. So let's have a look to some applications. That are here results for the Hernán map. The x-axis here is just some parameter where the dynamics of the Hernán map changes from regular dynamics to chaotic dynamics and vice versa. So the black line here are the results of the Lyapunov exponent, and the red curve are the results for the J measure. The blue curve here above is the border of the threshold of the significance level. Any result which is below this blue curve are significant on the 1% level. And one can see that any time the Lyapunov exponent drops below 0, also the J measure takes very low values. And if we are in the chaotic regime, the J measure takes large values, but below the noise level. Some other examples here. We can see the results for the Russell system for different parameters. Here we have period 1, period 2, etc. And then here we have the parameter settings for chaotic dynamics of the Russell system. Again, the black curve here are the results for the Lyapunov exponent, and the red curve for the J measure. So we are somehow mimicking the behavior of the Lyapunov exponent, but here without any kind of phase space reconstruction and any kind of parameter adjustment and these kind of things. The red stripe here again is the 1% significance level. Here are similar results for the Lorentz system. Again, here we have the Lorentz system parameter settings for the Lorentz system in the regular regime, and here for a chaotic setting. So what about the univariate case? In some cases you have only one time series and you're not able to construct it in a bivariate fashion. then one can create a second time series just by time lag. And that we did here for the logistic map, obtaining similar results. When the Lyapunov exponent shows regular behavior, the J measure takes quite low values. In the chaotic regime, we are below the noise level, but it takes quite high values. So the J measure indicates somehow the level of irregularity of the dynamics of the underlying system. That are here results again for the Lorentz, for the Rössler system and for the Lorentz system in the regular regime and the chaotic regime. And what we are showing here are the dependence on the time delay. So if we are increasing the time delay to very large values, it does not affect our numerical results. It is almost independent on this time delay. The green curve here are estimates for the X component of the Rössler system, the blue curve for the Z component. And what we can see here, this kind of oscillation are just the shadow of this oscillating behavior of the Rössler system. And you can see here that, the J measure is not an equivalent of the Lyapunov exponent, which is independent on the time series. Here we can see just some properties. In this case, this oscillating behavior of the X component of the Rössler system. Anyway, for each of the delay values, we can see that the J measure takes higher values, indicating chaotic dynamics in this case, and low values for the regular case. So what about noise? It should be robust to noise if you would like to apply that to any kind of time series extracted from biological systems, which are usually contaminated by dynamical noise and measurement noise. Again, here results for the Rössler system and the Lorentz system, the blue curve for the chaotic regime and the green curve for the regular regime or regular setting. And what we are varying here is the signal to noise ratio. And again, we can see that the Lyapunov exponent drops down quite fastly to 0, while the J measure seems to be very robust to noise, and it is almost independent on the noise level, although we are varying it within a large range. So that makes us quite optimistic for the application to biological systems. That is given in the next example. What we have here are the intracranial, the signal of intracranial electrodes of an epileptic patient. So that are the time. We can see here the time and seconds. In this vertical line, there's a line. There's the seizure onset and seizure offset. And of two different electrodes just implanted within the epileptic focus. And here are the bivariate result of the J measure and the two univariate results for the upper and the lower time signal. And here we applied this measure in a double running window approach. So we have here the running window in the time regime, and then we can estimate. We can also define a window in the frequency domain, just estimating the J measure of a part of this frequency range and shift the window along the spectrum, and that is shown here. The white area, the yellow area indicates results which we are not able to distinguish from the noise, and blue, white, and red colors indicate significant differences from that. So That is just one example from application. Just now we are trying to apply that for on different kind of systems, apparently high-dimensional systems where some kind of phase space reconstruction is hopeless. That is one activity. Another activity is that we do not know what is if there is some universal threshold where we can say that if the J values are below that value, then we are on the regular regime. If we are above, then we are in the chaotic regime. So it would be interesting to figure out if the threshold is changing from one system to another, or if there's some universal threshold for making such kind of decisions. So that is the state of the art of this work. And I'm very grateful to all of my collaborators and the students working together with me, and I'm learning very much from these people, and thank you very much for paying attention.
So this is probably a weird question, but a couple of months ago, I heard a plenary talk in German Physical Society where there was an example given in the context of ultra-fast pulses. And there the idea was also to split basically this complex wavefront into amplitude and phase. And the example was an audio example where the basically author of this presentation kind of replaced the phases of one piece of music with the phases of another piece of music, and then asked us to if we would recognize the music. And there were two examples. One was Mozart, Die kleine Nachtmusik, and the other one was Metallica. And now you should be able to tell me in which case we were able to recognize it.
Oh, so in one case you could recognize where they took the phases of the other, and in the other case not.
Yeah. Oops. So it's in the kleine Nachtmusik it was possible, and in Metallica not, because this basically noise, amplitude noise.
What was the motivation for doing this kind of experiment and this from this person? Why he did this? Wow.
Any further questions?
Yes, yes, 35 plus 5. Okay, so welcome back to the afternoon session. Today we, to start this session, so we have a first invited speaker talk by Chandan Dasgupta from IIS and ICTS in Bangalore. And he's going to talk about glassy dynamics, jamming, and dense persistent active matter. Thank you very much.
Okay, you can hear me, right? Yeah. Okay, so good afternoon, and I'll begin with thanking the organizers for this opportunity to come and participate in this conference to present some of our work. This work is going to be on dynamics of active particles, and in particular dense active particles, where glossy behavior, jamming, etc. become relevant. But my understanding is that not many people here are actually interested in glass physics, so I'll just go through the glossy part rather quickly, and then second half of the talk, I'll talk about some self-organization in this active systems, dense active systems, which perhaps will be closer to the interests of many of the people who are here. So this work was done mostly by Shumon Datta, who was a postdoc, and there are two colleagues, Pinaki Chaudhary and Madan Rao, who also were involved in this work. Actually, it is being written up, so it's a very recent work, and hopefully in a week or so, we'll have some preprint on CONMAT or archive. So a very quick introduction to active systems. These are very popular these days, so I'm sure all of you have seen some work or other on active systems. So these are systems consisting of objects which can basically move by themselves. Many of the examples come from the living world. So we have bacteria, fish, birds. Even these days people are trying to use these ideas to study a collection of people. And also nowadays a lot of experiments on artificial active matter, which are not living objects, but then people have devised different ways of realizing active systems in artificial matter. And so a lot of experiments going on, and many of these systems exhibit very interesting dynamics, collective dynamics. So that is basically the interest that we have in these systems. In particular, we will be interested in dense systems of active particles, where the physics of glass transition, jamming, etc. become relevant. So I will start with just one or two slides on what we mean by glass transition and what we mean by jamming. People who are not all that familiar with this subject. So glossy behavior is observed in liquids when it is cooled very rapidly, so that crystallization is avoided. So then if crystallization is avoided, then the system goes into what is called a supercooled liquid. And if you cool it even more, go to lower and lower temperatures, then it becomes amorphous solid, which is called a glass. So what one is interested in is basically the behavior in this supercooled liquid regime and how it becomes a glass as one goes to still lower temperatures. And in particular, today, what I'll be talking about will be mostly concerned with the liquid state. So we'll be looking at the supercooled liquids. And a very important aspect of the supercooled liquid is that if I look at the dynamics in a supercooled liquid, that becomes very slow as one goes to lower temperatures. So just one graph that I'm sure you may have seen. I mean, this is shown in most talks on glassy dynamics. What one is showing here is that as the temperature, this is 1 over T. So as one goes to lower temperatures, this quantity increases, and the viscosity increases by 14 orders of magnitude over a relatively small range of temperature. So this is one of the basic problems that one wants to understand. Why does the dynamics is becoming so slow in the supercooled liquid as one is changing the temperature? The structure doesn't change very much, so it's pretty much remains the same as a function of temperature, but in without changing the structure, the dynamics is becoming very slow. So that is the main problem in glassy physics. There is also these days a lot of interest in what we call jamming. Here, the temperature is not the variable of interest. The variable of interest is basically the density. One is looking at a thermal system. Basically, thermal fluctuations are ignored in the study of jamming. And what one finds is that if you look at a collection of hard objects, and if you compress so that the density is increasing, then one basically goes from a loose packing to a jammed packing where the freedom of movement of the particles is lost. So this is the jamming process. And one is often interested in the nature of the jam state, as well as what happens near the transition from the unjammed to the jam state as one is increasing the density. So these are the sort of issues that I have been talking about, I have been looking into over the last several years. And in particular, the question that we look at is now instead of having some passive objects, grains of sand, or in the case of glass transition, some standard liquid, if we have some system consisting of active objects, objects that can move by themselves, then how do these things change? The glassy behavior as well as jamming behavior, how these things change due to activity. And these questions are actually sort of basically motivated by lots of experiments. And as I have tried to indicate here, whoops, what happened? Yeah. Sorry. To go back. So here, I mean, there are many experiments, both on living active systems as well as in this artificial active systems, where one finds this glassy behavior in jamming as one is increasing the density or changing some other parameter like the activity parameter and so on. So the basic idea is basically is to try to understand the phenomenon that these active systems, dense active systems, exhibit near in the supercooled liquid regime or in the as one goes from the unjammed to the jammed structure and so on and so forth. So I'll just give you a couple of examples here very quickly of experiments on active systems. And what one is looking at here is a very recent paper. One is looking at a collection of bacteria, and basically one is changing the density, the packing fraction, and the characteristic time scale is increasing very rapidly. And there are two transitions here because the bacteria, they have 2 degrees of freedom, 2 kinds of degrees of freedom. One is the transitional degrees of freedom, other is the orientational degrees of freedom. So one could have a freezing of both of them, and the freezing occurs at 2 different values of this phi, the packing fraction. So this is very similar to the picture that I showed earlier, which is for sort of passive objects, standard liquids, where as you change the temperature, the relaxation time increases by several orders of magnitude. So this is one experiment. There are many other experiments like that. As far as jamming is concerned, I'll just briefly mention that there is now a lot of interest in trying to understand metastasis of cancer, the migration of cancer cells from one tumor to other parts of the body in terms of a jamming transition that takes place inside the tumor. And apparently, sorry, was there any question? So I mean, by looking at this jamming and unjamming, one can make a prediction about whether the cancer will spread to other parts of the body or not. So again, you know, these are of course cells are sort of living objects. So this is an example of jamming in an active system. So we have been studying this kind of phenomena, this glassy behavior, very long time scales, as well as this kind of jamming behavior in active systems over the last few years. And I'll just tell you a little bit about this glassy behavior and jamming, and then go on to talk about a special case where one sees very interesting self-organization. So of course, I mean, you know, we are looking at very simple models, not really cells. Bacterial cells, I mean, biological systems are very complicated. So we'll be looking at models where you have sort of particles which interact with each other through simple interactions. But these particles also, in addition to the interactions among themselves, have this active forcing, that there is this active force or self-propulsion force that act on all the particles. So that's the difference. I mean, here I have tried to mention that there are these particles and then there are these arrows which indicate the self-propulsion force that is acting on each particle. And this force has some characteristics. These forces will typically have a magnitude, and these forces change direction. So there is a time scale associated with the change of direction of the force, which is called the persistence time. So the activity is characterized by these two quantities, the strength of the active force and the persistence time. And in many of the systems, temperature, thermal fluctuations are not all that important. So basically, we'll be dealing with a thermal system, but these are the two parameters that will vary to find out how the behavior of the system changes. So this is one of the models, and I'll be talking about mostly this system now. Is basically a two-component mixture of particles interacting via Lennard-Jones kind of interactions. Two components because we want to study basically glossy behavior, jamming, or disordered structures. If we had only one component, then typically in 2 dimensions, they form crystalline structures, so we want to avoid that. So we basically have a two-component system, and this system is very well known in the literature on glossy systems. So now we want to understand how the behavior of this system changes when we introduce this self-propulsion forces. So it's basically Langevin dynamics. One is looking at this is the equation of motion, friction term. Then there is a interaction of the particle with all the other particles. In addition to that, we have this active force, which has a magnitude f and direction n. And there is a time scale associated with the changes of this, the stochastic dynamics of this direction itself. And that time scale is called the persistence time, tau p. Yes. Yes, so the Lennard-Jones parameters are different for the 2 different kinds of particles, and it's not additive. So that's what makes the system sort of, they don't phase separate so easily and they don't become crystal so easily. So they remain in the amorphous state for long periods of time. So this is the model. I mean, basically you have a bunch of systems in 2 dimensions, a bunch of particles in 2 dimensions. They interact among themselves. These forces are given by some Lennard-Jones potential. And then in addition to that, there is this active force. And active force changes its direction according to this equation. In 2 dimensions, this is a unit vector. So there's an angle. And the angle itself has this dynamics. And that defines the time scale tau p associated with this persistence time. So now, of course, we have a system which is given by these equations. Fix the density high to see this kind of glossy behavior or jamming. And then you just want to find out, what is the dynamics of the system at long times and so on and so forth. This is what gives you, I mean, there are many glossy features that one can look at. As I said, I'll sort of limit my discussion of that, but just show some kind of a phase diagram in this 2-dimensional plane. One axis is the strength of the active force, the other is the persistence time. And as I said, it's a thermal system. There is no thermal fluctuation. And one finds many different phases, liquid phase when the active force is high, a glass phase when the active force is low. And then when the persistence time becomes long, many new phenomena come into the picture. One is where you have intermittent behavior between jammed and unjammed system. Then one could have things which I call plastic turbulence or yielding and things like that. So today I'm not going to elaborate on this. This work has been published already a few years ago. And if anybody is interested, I'll be happy to discuss this even more. Today I want to talk about a special limit of this system. The limit is where the persistence time has been made infinity. So what does that limit mean? It basically means a set of interacting particles in 2 dimensions. And each particle also has some kind of an active force on it. And the directions of this active force are chosen randomly. But once the directions are chosen, it doesn't change further as a function of time. So it's a very simple system, a system of interacting particles with additional random forces on these particles. But these random forces don't have any time dependence. Once you have chosen a random force for a particular particle, that random force remains like that throughout. So basically then the question is what effect these random forces are going to have on the dynamics of the system when it is in the liquid state or in the jam state and things like that. Okay, so this is the basic system. And what one finds here is that in the limit in this picture, paper itself, there is some hint of that. When the persistence time is infinity, when there is no dynamics associated with the active force, then as you change the strength of the active force, one goes from a liquid state at high values of F to a jam state at low value of F. So there is some kind of a transition going from liquid to jam state as one changes the strength of the active force. So here is some simulation results that basically shows the occurrence of something like that. When the active force is large, like 3 or 2.3 or something like that, if I look at the kinetic energy of the system, it fluctuates as one would have that in a liquid. Liquid, the kinetic energy will fluctuate as a function of time. But as one goes to a low value of the force, then the kinetic energy basically goes to 0. System goes into a force balance state and remains in that state forever, and that is the state that we called a jam state. So there is this jamming transition occurring at some value of this active force. How much time I have? Can you tell me? 20 minutes. Okay. Okay. So so this is now what I'm going to concentrate on: the behavior of the system when the persistence time has gone to infinity. So just how these random forces acting on all the particles, how they change the property of the liquid, or they change the property of the active state, or the transition from the liquid to the active, to the not active, to the jam state. So there is, let's see if it works here or not. This is the movie, so I don't know whether, no, it is not showing. So what I was going to show here is that, if you start with a large value of F, when system is in the liquid, and then you suddenly change the value of F to a lower value, F equals 1, then how the system goes from a liquid state where all the particles are moving to a jam state where they become stationary. So that process, the movie is not showing, but that's what we want to study. Sorry. We want to study this behavior, that as the system is in a liquid state there, large value of F, and then we suddenly change the liquid state to a small value, and then it goes from this liquid state to a state where the particles don't move, they are force balanced, and this is the jamming transition that we are talking about here. So in the next 10-15 minutes, I'll just talk a little more detail about the property of this liquid state that one gets for large values of F, and we'll see that there are many sort of new things that show up in this persistent active liquid, which are not seen in standard liquids. So this is what we are looking at. Infinite persistence time, that basically means cell proportion forces on different particles are in different directions, but they do not change with time. Particles, of course, are interacting with each other. So now, of course, the cell proportional forces are going to affect the dynamics. One is still in a liquid state. When the force is large, one is still in a liquid state, but many properties of this liquid we'll see are quite different from the liquid that one finds in standard passive systems. So let's just start by looking at the structure. So this is basically the two-point function of the local density. And one finds that the two-point function of this liquid is actually quite similar to what you have in ordinary thermal liquids. There are this, if you are familiar with that picture at all, there are 2 or 3 peaks, and then eventually it goes to 1. And this structure is not all that different from ordinary thermal liquids. One also looks at system size dependence from 1,000 to 10,000 particles, and there is very little system size dependence of the structure. The structure, there is nothing much interesting is going on. So one then looks at the dynamics. And there, the first thing that we looked at was the kinetic energy. In the liquid, the kinetic energy, average kinetic energy of the particles, of course, will be non-zero, and there will be a distribution. So one looks at the distribution of the kinetic energy for different system sizes. And this was the first surprise that we found, that there is a very strong system size dependence of this distribution, which one does not find in ordinary thermal liquids. So this persistent active liquid, the system size dependence of this EK is much stronger than what one finds in standard liquids. So one has to understand that. Now, one understands from, let's say, studies of critical phenomena and things like that, is that when there is a strong system size dependence, that usually involves some length scale, some correlation length, which has become large. So if you have a large length scale, then whether the system is small or large compared to that length scale, that becomes important. And there one gets a very strong system size dependence. So basically, we looked at many other things related to this motion of the particles. So one thing we looked at is the velocity autocorrelation function. The velocity of a particle at time 0 and velocity at time t is, of course, a vector, so there's a dot product there, and how it changes as you change the time difference between the two instances where you're measuring the velocity. And first surprising thing is that, well, not just, I mean, in hindsight, it is not very surprising because there is a constant force acting on each particle. So what happens is that each particle acquires some non-zero velocity in the direction of the active force acting on that particle. And so the velocity autocorrelation function does not go to 0. It goes to a finite value. And at long times, the mean squared displacement is not diffusive, but it's ballistic, because each particle has a finite velocity in the direction of the active force that is acting on it. So again, this is not all that surprising, but what is surprising is that there is this strong finite size dependence. That, as you can see here, I mean, we are changing the system size, and as one is changing the system size, the value at which this curve is leveling off, that itself is changing with the system size. So this also says that there is some indication that there is some long length scale in the problem. And that long length scale we found in the velocity correlation function. So if I now look at not the time displaced correlation function, but equal time correlation function of the velocity at one point and the velocity at some other point in space. So this is that velocity correlation function as a function of the distance between the 2 points that one is looking at. This correlation falls off rather slowly. And as you can see here, if we look at the big system, for example, this red circles, it goes to distances like 20 or 30 in units of interparticle spacing. And the fall of this becomes slower as one is going to bigger and bigger system sizes. So it says that in this limit, the velocities, they get correlated in space. And as one goes to bigger and bigger systems, the range of this correlation is increasing. And we'll look at some correlation lengths, etc., as a function of system size. But this is the important thing, that the velocities of the particles get correlated over long spatial distances. And if one can measure from this fall of the correlation function some length scale, then one would find that that length scale actually is increasing as one is going to bigger and bigger systems. And this is, I think, shown here. This is the length scale associated with these velocity correlations, and as a function of system size. And if you look at the data points, and then one gets a pretty good power law dependence of this correlation length on system size. And in particular, the exponent is close to half. So it's a two-dimensional system. So exponent half basically means it's a linear size of the system. So these correlations, the range of these correlations is becoming essentially the same as the system size in this limit. So the velocities, this is the first sort of very big difference between this liquid and the liquid that one gets in ordinary thermal liquids, that here you have the system develops because of the presence of these active forces, correlations in the velocities. And these correlations, the length scale of these correlations actually keeps on increasing as you go to bigger and bigger systems in a way which is proportional to the length of the system. So if you go to the thermodynamic limit, this length scale will also become infinite. So infinite length scales, one says that it's sort of like a critical system. I mean, you're familiar with critical phenomena. So it's what this says is that if I look at the velocities, velocities are getting correlated over longer and longer distances. as one goes to bigger and bigger systems, and the system is in that sense critical. And this is actually, again, not very surprising, because people have found this velocity correlation functions becoming longer and longer range as one increases the persistence time. Here we are looking at persistence time that has gone to infinity. So again, it's perhaps not all that surprising that the velocity correlations will have a length scale which will increase with system size and will diverge in the thermodynamic limit. So this is the first characteristics of this liquid, which is very different from thermal liquids. Now, what I want to tell you in the next 5 minutes is something else which we found even more surprising, is that now you look at, instead of the velocity correlation function, you look at the correlation function of the active forces. Now you see that every particle has an active force. So from that, you can calculate, if you have the configurations from your simulation, from that you can calculate how the active force itself is correlated in space. And that correlation also is becoming long range. So this is very recent stuff. So it's not a very good figure, but the point is, one is looking at equal time spatial correlation of the self-propulsion force in the liquid, same liquid that I was telling you. And again, this correlation itself is falling off over slowly, and it becomes negative at long times. One can explain why it is becoming negative if anybody is interested. But the point is, again, here we see data for two different system sizes. One is 1,000, the other is 10,000. And you can see that the range of these correlations is increasing as one is going to bigger and bigger systems. So the active force themselves, they sort of self-organize in such a way, the particles self-organize in such a way that particles which have similar directions of active forces, they come close to each other. And as a result, they move together in some sense. It's easier for them to move together if the active force is active on all these particles are more or less in the same direction. So that is the reason for this self-organization. But I have not seen such self-organization in other contexts, in the sense that where you have random forces acting on the particles, and through their own dynamics, the particles rearrange themselves in such a way that this random but time-independent forces, they get correlated in space. And this correlation itself also goes to infinity as one goes to the thermodynamic limit. So that is the next slide. So one can get, sorry. Here, if you see these lines down to the data points, these are exponential fits. So from that, one can calculate some kind of a length scale. And one is showing that length scale in the next plot. This length scale as a function of number of particles or system size. And again, log plot, one gets a pretty good straight line, says that the length scale itself is proportional to some power of the system size. And the power is close to half. So this length scale also is essentially proportional to the linear size of the system. And as one goes to bigger and bigger systems, eventually this length scale would diverge. So again, the forces themselves are also arranging themselves in a critical way, in the sense that although initially when the forces were assigned, they were assigned in random directions. So they were not spatially correlated at all. But now as the system evolves in the liquid state, through its own dynamics, they arrange themselves in such a way that these forces acquire a correlation length, which is, of course, not just large, it becomes comparable with the system size. And as one goes to bigger and bigger systems, this length also will increase proportionately. So this is the new sort of phenomenon or self-organization that I want to sort of point out to this audience. Perhaps people will be more interested in that as compared to glossy dynamics and so on and so forth. So this is again reiterating what I just told you about. The self-proportional forces have random directions in the initial state. So when you start with the set of particles and assign self-proportional forces, you do it completely randomly. So there is no spatial correlation. So this is something like that. These are particles, and then I'm assigning this forces randomly. No correlation in space. But then in the liquid state, as the system evolves, it self-organizes in such a way that particles with similar directions of the force, they come close together in space, real space, and they move together. And so in the steady state, in the liquid steady state, one has a situation where the self proportional forces themselves become correlated in space, and this correlation length keeps on increasing as one goes to bigger and bigger systems. So in that sense, thermodynamic limits, this length scale will go to infinities. So again, in a very restricted sense, system is critical, but this criticality is happening because of self-organization. There is nothing externally. I'm not fixing a parameter that says that at this value of the force, it will be critical. For any value of the force for which the system is in the liquid state will show this kind of behavior. So again, loosely speaking, one can say that this is some kind of a self-organized critical system. So initially, you have this situation where everything is uncorrelated, but then in the steady state, you have this long-range correlations that I have just mentioned, and the range of these correlations keeps on increasing as you go to bigger and bigger systems. So in that sense, this is, I think, a new example of what one can call, I suppose. This self-organized criticality is something that is, in some sense, little controversial, but everything people try to say is self-organized critical. But I mean, here there is a situation where you are getting a very long correlation length developed by the system without fixing a parameter to a critical value, as you have in critical phenomena, phase transitions, whatnot. So I guess I'm more or less at the end of my time. Yeah. So there are many other things that we have looked at. I mean, I don't have time to go into it. I mean, here we talked about the liquid state, but now we have looked at the process of jamming as you take the liquid state at high value of f and then quench it down to small value of f, then how does this order develop? It is something like the development order following a quench in a thermal system, that if you take a system, thermal system, which undergoes a phase transition, order disorder transition at high temperatures, their correlation length is very small, but if you quench it down to a temperature below the critical temperature, eventually the correlations will become long range. So how does this correlation length grow, etc.? That's a process called domain growth, coarsening, and things like that. Same thing happens here. Sorry. Here, in the initial state, there is a correlation length which is very small, but then as you quench it to as the system evolves under its own dynamics, then this correlation length grows, and we have some understanding of how this correlation length is growing, and some analogy with the coarsening that you see in spin models when you quench the system from high temperature to low temperature. And then we have also looked at the jam state and how that jam state is different from the jam state that you have in passive systems and so on. But don't have time to go into all of that. So I just want to, this is one picture that shows this alignment of the active forces. So if you see here is the one is plotting the direction of the active force. This is a raster plot of that. And you see regions where the same color is there. And the same color basically means that in that region, the active forces are pointing in the similar direction. So this automatically shows that there is a length scale, and this length scale can be as big as proportional to the system size. So this is the message that I want to leave you with, that dense persistent active liquids, this is what we have looked at. Persistence time has gone to infinity, so we call that a persistent liquid. And it's dense and it's liquid state. I mean, the particles are moving around. But this system, although I mean there's a sort of this is a jargon name, it's actually just a collection of particles. It's different from the usual particle systems you deal with, in the sense that each particle was also a force acting on it, not the interparticle force, but some external force. And the external force is chosen randomly. But once it is chosen, then it doesn't change as a function of time. So this is just a simple system, but this system itself, through its own dynamics, becomes critical in the sense that it develops these long-range correlations. And so the velocities as well as in the directions of these forces. And I think this is, in some sense, a new kind of liquid that one would like to understand a little more, its dynamics. So I guess I'll stop here, and thanks for your attention.
Questions?
Thanks. So, Chandra, what happens exactly if you are set yourself at FC, critical value? Does the self-organization still go on there, or does the correlation length grow with some power of L? I mean, do you have?
Has not been studied in great detail.
I see.
So first of all, I mean, finding this critical value is not so easy, in the sense that that itself depends on the system size.
Okay.
So, and also, I mean, also to some extent protocol dependent.
Okay.
That if you start with a jam state and then increase the force, then it will become a liquid at some value of FC.
Right.
But if you start with a liquid and then quench it, it will become a glass or jam state at a different threshold.
Right.
So, I mean, all these things have to be taken into account. Sort of looks like a first order phase transition.
I see.
So, critical behavior near the jamming, whether it's there, I doubt it.
I see. Okay. Thank you.
Sorry. First of all, how do you measure the correlation length in this system?
So, basically, you have these particles, and each particle will have its velocity that you know, and each particle also has a active force on it. Its direction is fixed. The direction doesn't change with time. So you look at two particles separated by some distance r, and look at how close the velocities are. So you will look at v at equal time. V at particle vi dotted into vj, equal time, and there's a distance between I and j. So that gives you, I mean, then you average over all such pairs separated by some same distance, and that gives you a.
So it's the Euclidean distance.
It's the Euclidean distance.
Okay. So I just have another question. So two questions. Could you define an order parameter here, one, or now you just make a comment that if you come from two different phases, it look like two different critical point and two different kind of things. So could you see any signal of KT transition like KT transition here?
So that was what Shoto was asking, what happens near the transition. And we have not, as I said, there are some technical difficulties in tuning the system very close to the transition. So we have not looked at it in great detail, but it's possible. In the sense that, you know, I just want to point out this is coarsening behavior. This is kind of similar to the coarsening behavior that you would have in a two-dimensional XY model. Because one is looking at basically two-dimensional vectors, either the velocity or the direction of the active force. So, I mean, in a two-dimensional XY model, if you're at a high temperature, then the correlation is non-existent. But then if you quench it down to temperature lower than the critical temperature, then these correlations will grow. And there is this issue of vortices, anti-vortices basically annihilating themselves, and that's how the correlations will grow. So we are at present looking at whether here, in this case, I mean, if I look at these 2D vectors, then whether one can define vortices, anti-vortices, and how the dynamics of those things, and whether one can relate this growth of the correlation length as a function of time as some process involving interactions among these topological defects.
So it could be very much scale.
Could be. I mean, you know, one needs to see. Yeah.
Any more questions? I had a quick question. If, for instance, you change the initial condition and there is some kind of anisotropy or some bias in the initial force.
Okay.
So have you considered this case, or maybe some
fraction of
particle going upwards and others?
There could be a global flow, I mean, if you have a bias. So there is one situation where that happens, and which is sort of similar to this, a simplified version of that, is where, let's say, you have two kinds of particles, one with positive charge, one with negative charge, and apply an electric field. So one kind of particles want to go this way, other kind of particle wants to go that way. And if you start with a random mixture of this positive and negative, so at that point, there is no ordering of the velocities. But as a function of time, sometimes, depending on the parameters, system will grow into a state in which there is what is called lane formation. So one part of the system will go in one direction, other part will go in the other direction. So again, in that state, there are now long-range correlations in the velocity. But this is a simple version of this, in the sense, in our case, these forces are not just in plus x or minus x, they are over the whole circle. So it is difficult to, in some sense, say that, you know, in one part, all the particles are moving in this direction, one part, all the particles are moving in other direction. But there is a correlation in the motion. So that is what we find.
Okay, thank you. And last question.
Are your particles overdamped or underdamped?
Here we are dealing with the full Large-Van equation, but a few simulations have been done where the inertial term is left out, overdamped, and we don't see a very big difference.
Okay.
So inertia is probably not playing a very important role here.
Thank you.
Okay, so thank you again.
Thank you.
Okay, now we are. Yeah, perfect. So we are continuing with two short talks of 15 minutes. So we'll ask please to keep it brief, about 12 minutes plus 3 for questions. Okay, thank you. And the next speaker is Carles Tardio of Genomic Center of UNAM, and he's going to talk about plasmid evolution in bacterial communities and their stochastic environments.
Hi. Hi. I cannot see the presentation.
No.
Pantalla. Pantalla independiente. No sé. No. Voy a checar si te pones. Okay, here we are. Well, my name is Carles. No, yeah, it's okay. I'm a postdoc at the Center for Genomic Sciences at UNAM University in Cuernavaca. And yeah, I will be talking about bacteria, and specifically about antimicrobial resistance. You probably know that it is like a major health issue. So one of the things that we do in our lab is try to do some math modeling, trying to understand bacterial population. So this is like population dynamics. and the resistance of antibiotics. So I will be talking about this mathematical model that it's about plasmids. Plasmids are extrachromosomal genetic elements that carry information regarding the resistance of antibiotics. And this model is so easy. It has like bacterial growth parameters that encode the vertical transmission of information by the binary process of fission of bacteria. Moreover, it has like this conjugative transfer that accounts for horizontal transfer of information. These plasmids, these pieces of genetic informations can be transmitted horizontally, that is like horizontal gene transfer. And moreover, they can be lost through segregational loss. So if one plasmid is at one cell, then this cell divides. The plasmid can be lost from the subpopulation. And we also have like this bacterial killing parameter. And we have like this very simple model of ordinary differential equations that we can solve by one bacteria or by communities of bacteria. So we want to basically try to understand how plasmid populations can survive in different antibiotic environments, and this can be useful in order to understand this antimicrobial resistance issue that it's really a concern in hospitals and worldwide. So basically, we can do some mathematical computational simulations of these processes, and here are some very elementary dynamics. For instance, we have without antibiotics and with antibiotics, and we can see how the population of these both plasmid and plasmid-free bacteria evolve under different regimes. And we're interested in trying to look up for different time series and see how this plasmid population evolved. So we can basically investigate like really elementary dynamics, see in the linear regime, once we increment the amount of antibiotic, how the populations collapse, no? And we can moreover go into the cyclic or the kind of periodic time series. For instance, here I just put some examples with sinusoidal and Gaussian pulses, and here, for instance, with the square and triangle pulses. Well, in one case, we have in red like the plasmid fraction collapses to 0, and in another case, we have like the plasmid population survive. Okay, but now we can do the same thing, try to investigate the same dynamics, but in noise environments. So by trying to work with a very generic stochastic process, like the fractional Gaussian noise, we can create like violet noises. We can create, well, an amount from violet to Brownian noises and see how these plasmid populations evolve, and try to do some analysis on the correlations between the plasmids and plasmid-free subpopulations under the different antibiotic regimes. For instance, here we can see the cross-correlation between plasmid and plasmid-free bacteria. And for the Brownian motion, we see that it's decays more slowly, but it's slower, so they are less cross-correlated. And also we can move to the frequency domain and calculate the spectral power coherence, this time between the plasmid free density and between the plasmid density of bacteria and the environment. And we see here in the log frequency that also like the Brownian noise completely decorrelates with the plasmid bacterial density. And moreover, if we look at the correlation matrix, we see that, for instance, the violet noise, the one that has like more statistically independent variables, is more correlated with the plasmid subpopulation, and the Brownian noise is less. Oh, okay. It's less correlated with the the plasmid bacterial density is less correlated with the Brownian noise. Very briefly, we can move to some other kind of stochastic processes that can be useful in order to model anomalous diffusion. For instance, that it's like some situations that happen in real life in biology when bacteria form biofilms. They have like this extracellular matrix composed of polymeric substances that have a lot of viscoelastic properties. So this can be modeled with anomalous diffusion fractional Brownian motion processes, and we can try to replicate this kind of diffusion of an antibiotic into the biofilm. For instance, changing the Hertz experiment, the Hertz exponent of our fractional Brownian motion, moving into the normal regime of diffusion to the subdiffusion regime. No? Well, in general, the message is that these kind of processes are very useful in our in our tryouts to mimic what happens in bacterial populations that have these plasmids with antimicrobial resistance. And yeah, well, and in our lab, apart from doing this kind of math modeling, we also have like an experimental, well, we have built through the time a kind of hack lab with laser cutters, 3D printers, and the electronic workshop, trying to do some experimental work. For instance, here I show you we built a pipetting robot that it's able, for instance, like to replicate the time series that we studied through modeling, but experimentally. So for instance, no, if we have like this biodiluted noise antibiotic time series, we can replicate it by pipetting the exact amount of antibiotic through time that will be like the ones corresponding to the violet noise. And here in this case, instead of plotting some stochastic processes, we were working with plotting environments of antibiotic corresponding to elementary cellular automata. And this is an ongoing research project that maybe you can help us to get some ideas. And it's this kind of what we call bactomata, that it can be thought as an unconventional computing device, that it has like this co-evolving system, sort of in vivo fundamental biological entities, the bacteria, it's really simple, and also like that are evolved like in silico, well, not in silico, are evolved in vivo, but with an in silico fundamental algorithm that it's an elementary cellular automata. So the question is it possible that both domains are able to talk? And yeah, and we can do like the simulation of different elementary cellular automata time series of antibiotic in our model. And I guess that's it. If you have any questions, any suggestions, I'll be happy to hear it. Well, thanks.
In your last, one of the last slides, this experimental part, yeah.
Yeah.
I didn't understand. So you can put bacteria in different positions, but they do interact, or how is this?
Well, bacteria can.
How are you assuming that they can interact? Say.
Well, interact with the environment in which bacteria growth is determined by a cellular automata algorithm, no? For instance, we can think like without antibiotic, that's 0, and 1, in black, would be with antibiotic. and we can put this amount of antibiotic in this kind of 96 well experimental systems where bacteria are growth, no? For instance, during like 24 hours, and then some of these bacteria are passed into the next road. So we have like an experimental evolution of bacteria in time, but it's like conditioned by a cellular automata time series. So yeah.
Okay, thank you. Yeah.
Any more question? Okay, if not, let's thank Carlos again. So the next talk is an online talk. So it should appear soon here. And it is given by Inti Pineda from UAM, Azcapotzalco in Mexico City. And he's going to talk about phototaxis model in quasi one-dimensional channel. And so.
Let me share the screen.
Hello, Inti, do you hear us?
Hi, Professor. I'm here. Let me share the screen. Okay. Many thank you to the organizer. I'm going to talk about a work that Guillermo Chacon from UAM Guajimalpanay recently started collaborating on, and is phototaxis model in quasi one-dimensional channel. To start, chemotaxis is the complex movement of macroorganisms toward or against a chemical stimuli. And this behavior is very, very important because plays a substantial role in the seminal paper of Alan Turing. And on the other hand, the phototaxis is the movement of a motiled organism in response to light. And in phototaxis, there are much fewer works compared to those on chemotaxis, perhaps because in organisms that perform it are more complex in the sense of having photoreceptors in particular regions of the cells. For instance, here we have a Cyanobacteria cinetocostis, and the phototaxis of this bacteria has been widely studied in experimental conditions, and we can observe these kind of structures like fingers. Here the bacteria, here is a colony of bacteria, and the light is here, and you can see the fingers structures. This is a close-up, and in this close-up, there are a lot of bacteria in this apex, realizing the phototaxis movements. And several models have been developed in order to understand the dynamics of these bacteria. Agent-based models, stochastic models, and even models including partial differential equations. Here we have a seminal work of Galante and Levy. In this paper, they propose an stochastic model, and they, in order to obtain results, they realize several numerical simulations, and they obtained qualitatively the movement that we can observe in experiments. This here, the fingers structures. But the problem with this model that's that they solve just numerically. More recently, Chaviwadi and Kokolnikov simplified the previous model and using a stochastic model in order to take in a continuous limit and obtain a partial differential equation. This is the model. Here we have several probabilities. For instance, A is the probability that the bacteria jump or perceiving the movement and persists in its direct orientation. C, on the other hand, is the rate at which it moves after switching to a new orientation. This is important because the bacteria in biological conditions tends to move toward a gradient where there are more bacteria. Another probability is B. B is the probability to start or stop the movement, and D is the radius that the bacteria can identify another neighborhood bacteria. And Chaviwadi and Kokolnikov developed this stochastic model, and they arrived to partial differential equation, and this is the novel parabolic partial differential equation. These terms are similar to reverse diffusion and a long-term range. And here in this coefficient A, you can see the parameters of the models, the several probabilities. And essentially, in order to obtain this parabolic differential equation, they realize a symmetrization procedure considering the density of particles to the right, to the left side, and using the several quantities like this U and this eta term. Finally, they could obtain this partial differential equation. And the interesting thing is this equation, the complex equation, have a lot of analytical solutions obtained recently. So we can, people can obtain the Turing stability regime, and so the important things of this model is precisely the using in order to find the pattern of formation. But in biological terms, there are several ways to improve the model. For instance, the model is robust, but there are a lot of biological questions that one can introduce to the model. For instance, the growth of the bacteria populations from one side, the photoperiod in the probability of the persistence. And finally, you can improve this model making consideration about the heterogeneity of the environment. In this third topic, we are paying the focus of this talk. Essentially, the heterogeneity of the environment is considering confined regions, presence of obstacles, or in general, entropic barriers. In the literature, there are a lot of works recently made in order to model systems considering entropic barriers. And essentially, the idea is the following. This is the one-dimensional system, and in order to extend this model to another that considers the shape or the heterogeneity of the media, is introducing a width function like this. and compute the probabilities to the right side or the left side, obviously normalizing in each step. And in the literature, there exists specific procedures to do this. In this book, you can find the exact procedures about it. And essentially, the modifications are the following. The probability of persistence A is modified as this one. The probability C is modified as this. This is not a product. This is a function dependence. And where the probability to go to one side is directly proportional to the area. And in this picture, you can see that area to the right is bigger than to the left. So introducing these modifications, at least at zero order, we can derive the next partial differential equation. And you can see the next quotient. And this quotient is known in the literature as a Fick-Jacobs approach. And even in the diffusion term in A, you can see the slope and the width dependence of in the channel in the coefficient, the diffusion A. But unfortunately, the coefficients B and C remain to be determined. But in the original work, these terms is cancelled because U and B is quickly approaches. The condition of Turing stability is this. And we, after a huge algebraic work on self-reduction, we have to obtain a partial differential equation with the following structure. Is the
excuse me, you have 2 minutes.
Yeah.
It's okay.
We have to find this final partial differential equation. And as conclusion and perspective, the Chadi-Wadi and Kokolnikov model is robust and it's based on a stochastic model, and with a continuous limit is derived a partial differential equation that has analytical solution, and the probabilities of the model can be modified in order to introduce the effect on entropic barriers, which is noted as a Fick-Jacobs type approximation in the diffusion term. And it remains to obtain the dependence of the position in the nonlinear term and the forward terminated derivative. And this may be possible because it has previously been reported in the literature that for all the partial differential equation, as the harmonic equation, for instance, can be projected to one dimension, and the resulting expression contains the Fick-Jacobs approach. And once the PDFs obtained, the instability regime will be studied, and the suggested to the Guadalajara exponential expansion method in order to obtain analytical solution. And thanks a lot.
Any questions? Yeah, is there any possible experimental realization of this kind of problem in this kind of channels?
Yes, because in the culture of this bacteria, you can put the following barriers as maybe here with materials as plastic or kind of and other barriers here, and the size of this system is in the order of millimeters. So I think it's possible to realize experiments in confined regions using these bacteria models.
Okay, thank you. Any question? No. Well, if not, we thanks the speaker again. Thank you. And we'll have a coffee break and resume at 4 o'clock, I think, for the last short talk session.
side-by-side flexible plates in airflow. And please welcome Dr. Ancros.
Thank you. I will present to you laboratory experiments. I'm a teacher in the researcher in physics department, and my laboratory is next year. If you wish to have a visit later, you are invited. So the reconfiguration is about the wind in plants. What is reconfiguration? This is a phenomenon which make the plants deflect under the action of the wind. So this is a picture of the nature, but here are the laboratory experiments made by Gosselin. And this is a plate which is impacted by a cross airflow here. And when the fluid velocity is increased, the plate deflects more and more. So which are the pertinent parameters? The fluid velocity, the fluid density, it depends if it is water or air, the plate dimensions with the length and width, and the rigidity of the plate. And as always in physics, we like to make dimensionless numbers. So there are two dimensionless numbers, which are the drag coefficient, which is the force over the dynamic pressures by the area, and the Cauchy number, which represents the square root of the fluid kinetic energy over the elastic energy. So typically when the Cauchy number is increased, the deflection is higher and the force that air exerts on the plate is higher too. Which are the equations? We use the flexural moment. This is a Euler-Bernoulli theory. And the unique force which exerts on the plant is the force exerted by air. So we calculate the moment of the air on the plate. We equal the flexural moment, which represents the internal forces, the internal stress of the plate. And we reach to this equation, which is a non-dimensional equation. And using the boundary conditions, we can solve this equation and find theoretically the same profiles of the plate as in the experiments. So this was done previously. And what we want to do in our laboratory is, as the plants are not isolated when they are exposed to the wind, what the matter if two flexible plates are put in airflow side by side. Okay. So in my laboratory, I will put a plate like this. This is our laboratory. There is a wind tunnel, which is a recirculatory. The test section is 50 centimeters high, 60 centimeters width, and 1 meter long. And the velocity can go from 0 to 30 meters per second. Our experimental setup is the following one. We have two identical plates separated by a distance d, and the velocity can be varied. I don't know how to remove this, but the velocity will be varied between 0 and 3.5 meters per second, and the separation distance will be varied too. So here are the raw videos. They were not processed. And when there is only one plate, this is a video, and the air velocity is very low, so the plate is slightly deflected. When there are two plates, we cannot see them here because they are hidden. We see only one plate, but there are two here. And we see the same behavior. When the velocity is increased, the plate is more deflected. It oscillates very weakly. And when there are two plates, we can see that they oscillate in an out-of-phase way. And when the velocity is increased, the deflection is increased too. And the two plates follow on oscillating, and the mean deflection is higher than in this case. So this is a first finding that when two plates are side by side, the reconfiguration is not static anymore. So we measured the mean deflection of the plate. We measure the oscillation amplitude and the oscillation frequency. And we measured also the phase, the oscillation phase difference between the two plates. And we found that roughly they are more or less out of phase. For the mean deflection, we found that this is experiments when this is a Cauchy number. So this number here is proportional to velocity. And this series of points are for separation distances which are different. So the blue lines are for small distances of separation, and the distance is going from 2 to 6 millimeters. And we find that there is no difference between all these experiments. And theoretically, the deflection of one plate, one isolated plate in the flow is given by the green line. We see that this is roughly the same deflection. This deflection is weaker because the plate was were curved, slightly curved, so the deflection was lower. Now, for the oscillation amplitude, we found these curves. So this is the same axis. Here we have the Cauchy number, which is proportional to velocity, and the amplitude, the oscillation amplitude. When the plates are close enough, we see that they begin to oscillate from this value, and the maximum amplitude reach a value of 0.8 centimeters. When the distance between the plates is higher, the plates begin to oscillate for a velocity above a velocity higher than the previous distance, and reach higher amplitude too, and so on. When the separation distance is increased, the velocity threshold increases too, and the amplitude is increased too. And we see also that the amplitude evolution is not monotonous. There is a lot of noise, and I will explain this later. So this is what I said. And the third parameter we measured was the frequency. We see that the frequency for the closed plates is slightly higher than the frequency of the for distances, for higher distances. And when the velocity is increased, the frequency increases too. We could calculate the natural frequency for our plate. It was found equal to 1.45 hertz, which is near this value here. Okay, so we see that for low velocity, the plates oscillate with their own natural frequency, but when the airflow increases, then the frequency increases too. So these are experimental. This is an experimental study. So what we measured several characteristics. This is the conclusion. And we explained the strange behavior of the amplitude by the shading of vortices behind the plates, because behind rectangular plates there will be vortices which shade, and the vortices can be of different frequency and different structures. So the following step is a theoretical model, and we have to build it. So we have some idea, but we need theoretical physicians to help us. So if one of you is interested, you can come to see me. Thank you.
Thank you very much, Dr. Ancros. Very precise in time, by the way, also. Any questions? Yeah.
Thank you for a very nice talk. And I'm a theoretical physicist, not a theoretical physician. So I have a million questions about your talk, but let me just start with two, which is, first of all, with just a single, plate, is it possible that if you change either the size of the plate or the elasticity of the plate, that you can get non-steady response when you have a steady airflow?
I think the most probable is that it can occur when the plate rigidity is smaller.
Right, I mean, because I'm thinking about like flags flying and they're flapping all the time.
But even the flag fluttering is periodic when for the plates that we use, the flag fluttering occurs when the flow is axial. And when we take the same plates are ours, the fluttering is periodic, but it could be not periodic for another kind of materials. Yes.
And so let me just finish with one quick comment, which is, are you aware that there was experiments done by Michael Shelley at NYU about 25 years ago, where he had like a flexible thin rod and put it in an airflow, and he found that the drag force scaled as a 2/3 velocity of the size of the...
Yes.
You know this one? Okay,
yes, yes.
Very good. Thank you.
Any other question?
I've, of course, not much experience, but just wonder, do you know about simulations, how far they can go? I mean, just simulating the partial differential equations, or the model you are building up.
The interaction, the fluid structure interaction modulation is a little bit difficult because we have to input a flow, and then the structure will deform, and it will deform the flow again. So I think it is possible to make it, but I think it is easier to make a theoretical model to explain the phenomenon.
Thank you.
And do you have a physical explanation what there is a maximum in this amplitude in with the Cauchy number?
No, it was a surprise. It was a surprise. I expected to find an amplitude which would would increase, but I don't understand why there is a maximum and then the decreasing. I don't know.
Okay.
Then one question by myself. Do you think this might be related a little bit with synchronization? You know, this interaction between plates and airflow. Perhaps there is a specific frequencies in which this can happen, and after that, then you just go down with the amplitude. Some sort of resonances, perhaps.
Yes, it's an instability which can be seen as a resonance. Yeah. And now in our experiments, we found that the two plates have always the same frequency. But perhaps if we change the material, or if we went to a higher velocity, perhaps the frequency will be different. We didn't explore another regime.
Any other question? Well, if not, let's thank again Dr. Antros. Okay, our next speaker is Dr. Abraham Camacho Garibay. He is an associate researcher at the Ohio State University, and he will be talking about building a quantum trajectory simulator for studying strong field physics.
Okay,
thank you,
Aaron. Thanks for the introduction. First things first. Yeah, it works better this way. Thanks to the organizer for putting up this nice meeting. I'm going to give a short talk, which apparently is a good thing because I have been here often that whenever I give a talk, it feels like forever. So I think that 15 minutes is like a good amount of time for me. I'm going to talk about a project that's ongoing on right now at the Di Mauro Group, which is what we call the Quantum Trajectory Simulator. Sometimes we call it Selector, depending on whether the reviewer likes that name or not. But this whole title is a little bit of a mouthful, where I'm going to just quickly describe a couple of things that some of you probably don't need. But when we talk about strong field physics, what we mean is that the interaction of matter with a strong laser, meaning that the electric field of the laser is strong enough such that it can bend the potential that the electron feels. Actually, this is not, okay. Yeah, that's when we talk about a strong field. So when the potential is bent, the electron can tunnel out, and when it's in the field, it can propagate. And depending on the time it is ionized or it tunnels, it can come back or either go away directly. But if it comes back, it can interact with the core again. And there are several things that can happen. You can backscatter and gain more energy. You can recombine and send and emit some light, or you can kick out another electron. So The thing here, and something that I mentioned, is that it depends on the time that this electron is ionized. If the electron is ionized at some point, it may just go away. If it is ionized at some other points, it can come back at a later time, and the return time is going to also depend on the ionization time. So all these magenta lines try to convey the idea of a quantum trajectory. Unfortunately, we are kind of limited or bounded by the fact that we rely on tunneling. And it is kind of clear that the electron is going to tunnel more likely if the barrier is very suppressed, and not so much if the barrier is pretty much, well, no, not suppressed, or the field is not bending it. So this blue curve actually describes the tunneling rate that the electron feels, so it's very likely to ionize at the peak, but very unlikely to ionize as you go away from the peak, and even close to zero, it's just negligible. It just cannot happen. Well, reasonably cannot happen. Anyhow, so at the end, when you make your full measurement or calculation, what you end up measuring is the result of all these trajectories, either in the photoelectron spectra or in the high harmonic generation, high harmonic spectrum, or even when you calculate or measure your double ion yield, what you actually are measuring is the result of all these trajectories coming together. So what we would like to know is, well, what happens if we can just get rid or let loose of this bound, this limit that the tunneling ionization rate has? For that, we will need to bypass this ionization step, and the way to do it is by using an attosecond pulse train. In this case, each blue line represents a different pulse, which are at the same pulse where we can move the delay back and forth. So instead of relying on the tunneling, what we are doing is having a single photon absorption such that you put the electron out there and then it gets propagated by the field. Effectively, what we are doing is just selecting one of these trajectories within a certain error or tolerance. And for these, we need several things. The requirements will be that we need our infrared sources to be long wavelength, such that most of the dynamics is actually given by the field. So we need 1.7 micron or 2.4 micron, and we need an intense XUV light, such that most of the ionization is actually given by this attosecond pulse train, and not so much by the tunneling. We also need that these pulses are narrow-ish, because if you just have if you want a pulse and you want to control very well the time that your electron gets ionized, that means that pulse has a broad band, a bandwidth that is very broad, such that it can start with whatever velocity. And we don't want that. We want to have a good knowledge of when the electron is ionized and a good knowledge of the initial conditions of these electrons. So we cannot have a very broad band, but we can also not have a very narrow band. We have to be able to control the delay over between the attosecond pulse train and the infrared, and this has to be fixed and repeatable. So if we do all these, we will be able to, in principle, see differences in any of our measurements of our observables, such that we can, in principle, extract information from each one of these trajectories. If this is not motivation enough, I'm just going to very shamelessly put a plug on here, because Professor Agostini actually talked about this project in his Nobel talk last year, and he was very gracious to put the faces of some of the people that have been working on. So for completely unwarranted, my face appeared in that talk, and I just like to show it up wherever I go. So quickly, just this is kind of an overview of how this apparatus works. This is pretty much one of the current view of the apparatus. There has been some updates to it, because this has been a long-standing goal of the group, and it has involved the work of a lot of very talented people and also some undergrads, which include, for example, Andrew Piper, Dieter Kiesewetter, and Joel Liu, and also this very talented experimentalist, Jiawo Tang, who spends half of his time in Ohio State and half of his time in SLAC. But long story short, usually, well, the apparatus in a nutshell just has an infrared laser that it's split. Part of it is brought to a generation chamber where it's made to interact with a gas or a material. The attosecond pulse trains, or the XUV light that it's generated here, is passed through a filter such that we can further shape the pulses, and at the end they are recombined and put together, and then we can do our experiments here. Okay. As I said, it is important to have a good control on the XUV pulse. For that, we have several schemes to generate this. And actually, again, I cannot praise Jiawo Tang enough. He actually came with even more ways to produce these pulses because, for example, if we want to study helium, we need very high energies, and for that we usually use xenon. And you may know this or not, but xenon is mainly produced in Ukraine, so right now it's kind of very expensive. So he came up with a novel scheme where he used a two-color pulse to generate these pulses, and he can produce still very intense attosecond pulse trains that can ionize helium. Only that now the harmonic orders are even not odd. That doesn't really matter much. The good thing is that then we can see that, again, one of the requirements is that the XUV is actually driving ionization. And here you can see what the XUV alone will do, not much. Here in red will be what the IR only will do, again, not much. But when you put them together, you have 2 orders of magnitude more electrons in your measurement. So, and again, you can see that there is a very strong dependence on, or a very strong sensibility with respect to the delay. So far I have told you that we have already control on the ionization and in the XUV, but so far we still don't know the time, let's say. We know that there's an oscillation here, but we don't, but in principle, I cannot tell you which time is where the field is 0 or the field is maximum. And that can be actually determined first as kind of a well-known set of principles or equations that will be the streaking experiment. That just means that you ionize in a laser field, and the best moment to ionize, if you want to give the electron the most energy, is when the field is 0 or the vector potential is maximum. But anyway, we need to have a better control on this, so we can compare the experiment with the TDSC, and it is important that we actually have all the phases of the pulse included in here. If you learn anything in the morning session, is that phases are important, really, really, really important. So it is really fundamental that you have your pulses very well characterized in order for the TDSC to reproduce what you see in the experiment. And in particular, you can see that here, if you fit the maxima for each energy at different energies, but if you fit the maxima or delay at which the maxima appears, you see, especially at long wavelengths, that you have 2 kind of flat regions. This flat region at the beginning or at low energies it corresponds to streaking electrons here. Okay, streaking electrons. And then later on, there is a quarter cycle shift that corresponds to electrons being ionized close to the peak, because those are the ones that are going to be coming back and backscattering with the highest energy. So by having these TDSC results, we can pretty much be certain that we know the field of our laser at any given delay. By the way, it should be noted that these TDSC calculations are for just one single intensity, while in the experiment you have, well, the focal averaging. but still the agreement between experiment and TDSC is very remarkable. Okay, so we already have here the electron spectra with respect to delay, and we can use this to, I don't know why I have to point that way. Okay, and you can extract the phase of the infrared field knowing the maximum of the electrons. This is what is giving us the maximum of the vector potential or the minimum of the field. And here now you can see the ion spectra of the doubly charged ion. And the first thing that you should notice is that when the electron are maxima, is not where the maxima of the doubly charged ion is. The doubly charged ion is shifted by a certain delay. The funny thing, or the interesting thing, is that the maximum is actually appearing at 0.3 infrared cycles, which is the classical result for the return energy for the electron, the return time of the electron of the highest energy. And there are couple things that you can see here that maybe will give you pause. The first thing is that this doesn't look very sharp, and the other is that there is an offset. The fact that this oscillation is very wide actually has to do with the shape of the pulse. Again, we can extract it through some measurements, some characterization. And when we do that, we can, by convoluting the cross section, the ionization, the doubly charged ionization cross section with the pulse shape, you actually have this really good agreement with the experiment and theory outside of this offset. This offset actually is something that we don't fully understand. It seems to us that when you excite or ionize, part of your XUV is actually exciting population in long-lived states that then can just ionize anywhere. So this is an extra point that we are looking forward to investigate a little bit more. And I am running out of time, so quickly just I'm going to mention that we also want to push this technique further in order to also try to extract information about the particular trajectories that you can get and maybe have a kind of tomographic information from this spectra. And with that, I will just finish by acknowledging all the people involved in this project, mostly in Ohio State, but also in LSU, in the State University of Louisiana State University. With that, I will look forward to your questions.
Questions? Yep.
Yeah, thanks a lot, Abraham. Very nice. So what's actually the difference in the physics compared to the original streaking experiments where you have a isolated attosecond pulse?
Okay.
No, like Krauss and whatever the famous, and now you do a train. So what's different there?
Okay, maybe I'm wrong, but I think that the original Krauss experiment has energies well above threshold, right?
Yeah, it has, but I mean, essentially, you get basically your ionized electron streaked, as you say, by the infrared field, right? That's kind of the same thing you also do, or not?
Here.
So do you actually you do not ionize by the XUV pulse, or do you do?
We try to put it as close to threshold as possible.
This is Andelier. She did this also 2007, I think.
Okay.
And then you get chaotic trajectories. It's kind of interesting what happens there, because you get trapped depending on the phase or not.
Yes. Now, I do not know how well she controlled this timing or this delay, because also the problem, as I said, one big chunk is having a particularly well sculpted XUV pulse, because you can have something very narrow where either you can just how can I say it? You will have an interplay between the temporal resolution and the energy resolution. And I think that what we are trying to push here is have an optimal combination of both, such that we can sample the return electron. So the thing here is that, as you said, there are some trajectories that will be kind of trap or chaotic. That's perfectly fine. But the thing here is that we want to see what happens at the recollision, and I think that that's a little bit more complicated, because here the goal was not the electron spectrum by itself. The goal was the doubly charged ion, and the doubly charged ion and the dependence and the time difference with respect to the ionization time is what we are trying to look at.
So you want to create a classical electron as much as possible.
Yes.
So then you need to consider that in phase space, in E and T, right? Then you have a phase-space distribution of your electron in this space, and that should give you an optimal, I don't know, Gaussian or whatever.
From theory, yes, we can go there. So however, what I'm trying to do is reproduce the experiment as well as they can do, because no matter what they do, they cannot do a Gaussian XUV pulse, I suppose. They have these filters, they have these other things that are going to put some phases that can make the pulse less optimal.
Wouldn't they need to do as much as possible reproduce your GDSE, at least for this goal of the simulator?
Okay, there are following up things that we're doing, but let's say that we're in like a feedback loop here. It's not just they saying what to do, because also Ken Schaeffer is also deeply involved in this. So there is a continuous feedback about how to do it, where to do it, how much energy to put there, all that.
Any further questions? Okay, if not, then let's thank Hernán again. Our next speaker is another local. He's Adrián Ortega. He's also an associate professor here. He will be talking us about benchmarking quantum computers with the protocol of quantum state matching.
Okay, thank you very much. So today I'm going to talk about the work that I did in the postdoc at Wigner Institute in Hungary, which was also part of the National Laboratory of Hungary last 2 years. So first, let me begin starting introducing the group. So I did this work mainly with Tamás Kiss, which is also in the audience here, and with Orsia Kalman, which is also in the Wigner Institute. And we recently have some big feedback from the Duke University in the US. Unfortunately, these results, these experimental results, are not yet ready. So everything that you are going to see, it's on this lower side, which is companies provided quantum computers. So we have IBM, IonQ, Rigetti, and the Oxford quantum computers. Okay, so by now the field of quantum computation has grown quite much. So essentially this is a table that shows more or less where to fix this talk. So you can see that here that there is a lot of software going on, a lot of physics in the superconducting qubits, for instance. But then my talk is going to be focused on this level, which is mainly quantum circuits and the output that you get from the measurements from the quantum computers. Okay, so we are in what people call the NISQ era, so noise intermediate quantum era. So we have quantum computers, they are very noisy, so we want to know what to do with them. So what are they used? Because there are important questions, either from the technology side or in the investment side. For instance, which technology is more promising? You have, for instance, superconducting qubits. You have ion traps. Mainly, these are the two that we studied. And some questions which are natural is, for instance, which is the universal system? Is there a universal system? Or if there is no universal system, then for which type of task we can aim to solve or quantum computers with a certain technology. And also which types of tasks are worth investigating in this NISQ era, where you have imperfect quantum computers, etc. So of course, in order to decide these matters, you need to somehow benchmark or to do a quality check of what is giving you the quantum computer. So how do you do it? So many questions, for instance, is a single number enough? So in general, the answer is no. You need a certain matrix in order to decide which, in order to measure different characteristics of a quantum computer and to decide if it's behaving correctly or how wrong it is behaving. You also have to define what are the characteristics of a good benchmark. And with this, you can maybe exploit the knowledge that is already known in classical computation, right? So in terms of how to, we have that the field is can be kernel divided essentially in two areas. One is the circuits which are based on randomized benchmarking. Yes, so these so-called quantum volume or mirror circuits, or you have the task of certain hallmark protocols. For instance, I don't know, quantum computation protocols, quantum chemistry. So what I'm going to show, it falls more on this category on the left side. And now, what are the characteristics of a good benchmark? Of course, the good benchmark, the best benchmark, is the user's own application problem. Yes, so you want to know a task in a computer. You want to solve your task, and you want to know that your data that you receive it's good enough for your purposes. But then you also have industry interests. So essentially, it is said usually that in industry they are more focused to their own interests, but in academia we are like more open and ready to accept criticism, etc. Okay, so what would be a good benchmark, for instance, from the point of view of classical benchmarking, but also one can see that this can be translated to the quantum case. So we are now in the stage of performing performance benchmark. So it means not even performance, but quality checks. So I put a circuit, and I want to know how close the results that I get are good enough so that my theory matches the experiments, right? So there are other characteristics, for instance, that the workload has to be representative for real-world applications. You have to exploit all the capabilities of your quantum computer. Of course, you cannot tune your device for certain specific task. And this has something that has to do with, for instance, some news that were a couple of years ago with quantum volume Honeywell. You have to generate reproducible results, and you have to have, obviously, non-inherent scalability limitations. So for instance, the quantum volume, which is too popular these days, is in general not scalable. So specifically, the way we test the quantum computers is using this protocol, which was designed initially by Tamas and Norcia in 2018. And it's based in something that is called the iterative dynamics, which generates complex dynamics on the complex plane or in the block sphere, and that it can generate very trivial null dynamics. For instance, it can generate chaos or these type of things. So the idea is very simple. You you prepare one state, which is just characterized by this Z, which is a quantum number. You prepare 2 qubits in the same initial state. Then you do an entangling unitary, and then you do a post-selection. So based on the measurements that you get, if you measure 0, then you kept your result, and then what you are going to get is this transformation of your initial state with where this fz is, in general, a nonlinear function. So and this is the type of things that we want to exploit in a quantum algorithm. So essentially, this was just one step, but you can do it several steps iteratively, and then after n applications of this protocol, you can get a composition of this complex function, which is in general not linear. And if you're interested in this type of things, there is some talk by Tamas on Thursday, and also Attila spoke a little bit in his poster. Okay, so for us specifically, the protocol we are thinking about is this very simple transformation, f z squared divided over epsilon. So the task is that, imagine that you have a reference state, which in this case is going to be 0, and this is the state that you want to get after a quantum computation for some reason. And then you want to decide if the state that the quantum computer gives you is close to this initial state, or it falls outside some prescribed neighborhood. So here the epsilon is going to tell you how close you are. And if you are inside this area of the circle epsilon, you are going to accept all these states as good states. And then what it does, this protocol, in a certain way, is to correct the state that you get. So for instance, if I get a state here, after a few iterations of this map, I will get closer and closer to the reference state 0. So this is just particular things. This is the entangling unitary that implements this map. This is the decomposition that we put in the quantum computer, and this mapping has certain characteristics which are good for us for testing the quantum computer. So for instance, the map is super attractive, so it means it converges rapidly to the reference state or to the orthogonal state, which is state 1. Also, we can test 2 to the n qubit, yes. And the most important thing is that this protocol doesn't have a quantum overhead, because I can check very easily for a Hilbert space of 2 to the n, the classical result that I should get, because I just have to do the classical iteration of this polynomial, right? So, so the goal then is to benchmark the quantum computers using this quantum state matching protocol. And essentially, the first experiment that we did was to try to distinguish between statistical errors and device-specific errors, because the statistical errors are something that you inherently are going to have, because the quantum mechanics is statistics. So you have to separate the noise from the trials from the actual noise or the actual errors that are in the devices. So essentially, this is a crude approximation of how the errors are going to scale. And then we do this with a figure of merit, which is the success probability that the protocol does what it has to do. And one thing to notice is that this quantity does not depend on the initial angle phi, which is the latitude. It only depends on theta. Yeah. So this means that if I fix theta, all the angles phi theoretically they have to give me the same success probability. And this we are going to use it for benchmarking the quantum computers. And well, if you have an experimental quantity, then you have the theoretical quantity that you are expecting, and then a certain threshold that is given by this standard deviation. Okay, so these are the first experiments that we did. We took 2 quantum computers from IBM. They are very different in the sense that IBM reports that, for instance, Manila has a quantum volume of 32, and Lima, which had a quantum volume of 8. And this means that you expect that the results in Lima and in Manila are very different, with the Manila close to the results that you are expecting. So here in the above plots, you can see as a function of the initial angle, the success probability, the theoretical, which is the thick blue line, and the threshold up to 3 sigma, and the points are the results from the 2 quantum devices. And you can see here 2 trials. Well, this is just fixing epsilon equal to 0.7 and epsilon equal to 0.8. And the difference between these 2 is that here we have an average over the initial value of the angles. And then this value of the angles, we took it differently. In the upper row, we took it to be equal space between 0 and 2 pi. So this is a very well-ordered initial state. And on the bottom, we have random initial angles between 0 and 2 pi. So the first, let's say, main takeaway of these 2 pictures is that when you use random angle or random initial states, you can see, for instance, that the Lima and the Manila devices behave very, very similarly. So this means that if you do a random testing, it's going to hide away many specific errors that, for instance, you can get when you do not do this. Like, for instance, here you can see a clear separation between the 2 devices. Yes. Okay. We also are working in a gate-based metric. So here in these plots here, we fix the angle, the theta angle to be pi over 8, and then we vary the phi 0. And if you remember, then this phi 0 should be, all the success probability should be equal, and this represents these gray lines here. So they should be equal for all the devices. This is for one step of the protocol. this for 2 steps of the protocol, and then here you have the statistical uncertainty, and you can see the results for several devices. So essentially, in the data that we collected, we do not have we not only have like a random signal, but you can see that you have some random that you have some structure data, which is represented by these lines here. Yeah, so you have some extra oscillations that you may want to describe and see how they are coming from. And so far we are working in this model, but we can say that it's based on a noise and a noise model based on the gates that are actually used on the protocol. And it's nice because you can see that many of the data is described on average by this noise model that we have here. And of course, you can do a statistical benchmark. And here we just have a proposal, which is to measure as an average between the success probability theoretically minus the success probability experimentally. And then here we just gather the behavior for different quantum devices. And you can see here the different technologies. Here you have IBM quantum computers. At the bottom you have IonQ, which is essentially better in all cases. And here at the top you have also superconducting quantum qubits, which are not from IBM and which are a lot of more noisy. And yeah, essentially this is our work. So we have some advantages in the algorithm. That is a highly structured circuit, meaning that it has fast transpilation times. There is no classical overhead, which is important. We can test 2 to the n qubits. And in the experimental side, we have, of course, time variations scanning the initial state, depending, yes, it's the initial state. And we found that evidence that the random initial states hide away some errors that you can see in other cases. And I didn't emphasize enough, but you can see in the plots that the quantum volume does not follow our classification. So there is still more going on than just classifying quantum computers with just one number. And in general, for us, the trapped ions are the best technology so far, which is to be expected, which is also nice. But also to be emphasized that the IBM is more or less, you can have very good quantum computers, but you can also have not so good quantum computers with this technology. That's it.
And does anybody would like to ask a question to Ariane?
I'm curious about your entangling operation with the parameter epsilon.
Yes.
And where does it come from? Is it based on certain interaction, physical matter system or something like that? And also, your algorithm is sensitive to how well you can implement this gate, because usually it happens that entangling gates or qubit gates suffer from certain fidelity. They have not perfect fidelity as well. So is it also very important for your purpose that you can reach a very good fidelity in this gate?
So in the first question is yes. So essentially you can decompose this U epsilon into an interaction between the qubits with X and Y operators. So this is the physical interaction I would say that is working here. And well, you can further decompose it in the C nodes and local gates. For the second question, yes, it's very important to have high fidelities, but there is also like this trend that the companies are starting to develop a lot the fidelity in the individual gates. But right now, I would say that is not quite known how much the fidelity acts when you have a certain algorithm. It's not just that you test one gate. If you test the whole algorithm, your fidelities can affect a lot, and also classical errors, the coherent errors. So The difficult thing is that everything is in the mixed.
Okay, thank you.
Simply, I didn't see that number. I mean, the idea is to check n qubits by repeating that map n times, right?
Yes.
So how large can n be, or in your experiments, what was the what was n?
Oh, here is a very simple experiment. It's only one step, which means 2 qubits, and 2 steps means 4 qubits. And this is the more that we can do in the free IBM machines. We couldn't test more steps.
That is beyond that, the signal is lost essentially.
Yes, and also you have to pay for use more qubits.
I see.
Yes.
Okay. Thank you.
You mentioned something about classical overhead at the end. I was just wondering, like, what type of overheads there are.
So the most popular is the quantum volume, and for drawing the benchmark of the quantum volume, you need to test essentially classically the whole probability distribution of your outputs. So you have to measure 2 to the end bins, and then you have to decide how well your experiment fits these 2 to the end bins that you have experimented. And this is hard. I mean, at some point you will not be able to do quantum volume in classical computers.
Thank you.
More questions? Then if not, let's thank again Adrian. Okay, our next speaker is Dr. Claudia Martinez. She's doing a postdoc in Universidad Autónoma de Guerrero. She will be talking us about stability mapping of bipartite tight binding graphs with losses and gain, PT symmetry, and beyond. Please.
Okay. Hello, everyone. I will present the result of our work titled Stability Mapping of Bipartite Tie-Binding Graphs with Losses and Gain, PT Symmetry, and Beyond. This work was done in collaboration with Moreno Rodriguez, Mendez Bermudez, and Henry Benisti. Well, in this work, we consider bipartite tie-binding graphs composed by n nodes splits into sets of equal size, one with nodes with loss and the other nodes with gains. The nodes are connected randomly with probability alpha, and depending of the graph configuration, the non-hermetic Hamiltonian can present pseudo-hermeticity or PT symmetry. In both scenarios, the spectra of the non-hermetic Hamiltonian can be real. So, the model that we use in this work is bipartite tie-binding random graph composed by n nodes splits in two sets of equal size. One set contains nodes with loss and the other nodes with gains, how we can see in this figure. And depending of the parameter alpha, there are more or less connection, and the Hamiltonian looks like in this way. If alpha is equal to 0, we have only a diagonal matrix, and if alpha is equal to 1, we have two blocks out of the diagonal. Gamma is the loss and gain strength and is real and positive. Okay, the tie-binding Hamiltonian of our model can be written in this form, has the equation 1, and in a matricial form, we can see in this way. The elements of the diagonal are random number of the normal distribution, and an example on we can use our model is in photonic, specifically in couple metasurface, as I show in this figure. In this, we have two metasurface, one with gains and the other with loss, and we couple unit gains with unit loss. In general, our Hamiltonian is not PT symmetric, but if U is equal to U transpose, the Hamiltonian is PT symmetric. Here, I show some configuration in which the model is PT symmetric. So, for large size of the networks, we can diagonalize the Hamiltonian analytically. However, we can see that H squared is of this way, and we can see H squared is real and symmetric, so its eigenvalues are real. So the eigenvalues of H are real or imaginary, how I can show in this figure. We can see that depending of the parameters, the spectrum can be real, as is the case of the higher values of alpha and lower of gamma, and can be imaginary if we have a low probability of connection and a higher value of gamma, how we can see in these panels. Here I show the spectrum of the Hamiltonians for different values of alpha and different size of the networks. We can see the panorama is very similar. The red points are the real eigenvalues, and the blue points are the imaginary eigenvalues. And we can see that the real eigenvalues are bounded for this expression, which is according to the semicircle law. And the imaginary spectrum is bounded for gamma. So we also study the fraction of real and imaginary number of eigenvalues. And we plot the fraction of imaginary eigenvalues for different values of gamma and different size of the network. Each panel corresponds to a different size. And we plot as a function of the connectivity parameter. And we found that the curves have an initial exponential decrease, has the black lines, followed by a power law, has the red line. And numerically, we found expression for these fractions and for the fraction of real eigenvalues. And with this expression, we construct a stability map. In this figure, I show the fraction of real eigenvalues in the gamma alpha plane for different sizes of the networks. And we found an expression for alpha critical, which is the value for the proportion of real and imaginary eigenvalues is equal. And I mark this with the dashed lines. And numerically, we found this expression for these lines. So we studied bipartite tie-binding random graphs with balanced on-site loss and gains. The model is characterized for 3 parameters: and the size of the network, alpha, the connectivity probability, and gamma, the strength of the losses and gains. By analyzing the symmetries of the Hamiltonian, we recognize pseudo-hermeticity and PT symmetry, which might produce real eigenvalues even when the Hamiltonian is non-Hermitian. As future work is interesante to study the eigenvectors and dynamic of systems that present this difference in their eigenvalues in both real and imaginary spectrum regimens. And here some reference for this work. Okay.
For your talk. Does anybody would like to ask a question? Yep.
I mean, in general, you don't have PT symmetry, right? So if you just choose a random Hamiltonian, it will not be PT symmetric. But is the probability that it is PT symmetric finite, or is it small or large, or?
It's small because we need to do that if, for example, B is the second node are connected with the 4 in one set. The first set should be connected with the second, and there are less configuration for this case.
Yeah, I see. Okay, thanks.
You had a red and blue figure where you plotted the real and imaginary part of the eigenvalues. That figure, yeah. But I couldn't read what you plotted. What you actually, I don't understand what you actually are plotting.
Okay, these are the eigenvalues of the model. The red points are the real eigenvalues, and the blue are the imaginary eigenvalues for different values of alpha. and different values of n.
But are all eigenvalues either purely real or purely imaginary?
Red real and blue imaginary.
Yeah, but are there no complex eigenvalues?
No.
Why is that?
We found that in this model, the eigenvalues are real or imaginary, but not complex.
But what is the reason? Is there a symmetry?
Yes, the square of the matrix is real and symmetric, so their eigenvalues are real. So the eigenvalues of H are...
Okay, that's clear. Thank you.
Yeah.
Why is it important? I mean, why is it particularly important that the concentration of real eigenvalues should be 1/2 at the critical point? And I'm also puzzled because if that is 1/2, then somehow the imaginary eigenvalues will have a quarter up and a quarter down. Is that correct? Since they come in pairs.
Can you repeat, please?
Sorry. So imaginary eigenvalues come in pairs.
Yes.
So when you have 1/2 real, then the other half is a quarter up, a quarter down.
Yes.
Is that the correct interpretation?
Yes.
And why is the important 1/2? That's the other question. Why does 1/2 play a special role?
The parity symmetry.
Oh, that's the one that's PC symmetric. Okay, thank you.
Yes.
Anybody else would like to ask a question? Okay. Yeah.
I mean, the PT symmetry you can check with U, right? With the matrix U. But also if the fraction is 1/2, I mean, is it certain that if the fraction is 1/2, then you always have PT symmetry?
No.
It's typically like that. You're not sure?
I don't know.
Okay, thanks.
Okay, then thanks again to Dr. Claudia. Very much. Two announcements. If any of the participants would like to have a physical certificate of their participation, please tell us. We can give it to you now. And the second question, by tomorrow, if there is some invited speakers that have are using Markus system and they are presenting with this, could you please tell us in advance so we can more or less arrange so these things that happen today that we don't have volume and stuff like that could be solved before? We will appreciate it a lot. So thank you very much for our today meeting, and I think we close. There's another talk?
Yes, only.
Okay. Sorry. So who's this? Because it is not in the... We have another speaker. He will be online. He's Mario Estrada. He's from Tec de Monterrey, Estado de Mexico. Mario, we will appreciate if you can help us sharing your screen. Pero no ha compartido pantalla. No está. Okay, Mario's another round. Okay, then, well, I guess we will have to stop here. And, well, thank you very much for your participation today. And we meet tomorrow again.